All right, can you see the screen?
Fantastic. I can see your screen.
Okay, well, great. Well, welcome everyone to the PCI Level 3 School. As Lauren said, my name is Steve Qualls, and I am with Ross Bryan Associates. Been with Ross Bryan since 1995. Uh, Need to update my slide here. I'm currently the president of Ross Bryan, and over my years here at Ross Bryan, I've spent a good bit of time auditing PCI plants for certification, as well as designing various structures and serving on PCI committees and teaching these classes. So welcome, and if I can be of any help to you through this process, feel free to ask as we go along, even outside the class. If I can ever be of help to you, feel free to reach out to me. But that's me. Also, we'll have teaching this week. Chance Sudbury. Chance has been with Ross Bryan since 2012. Has done a significant amount of audits during that time, as well as does a lot of design work for the various projects that we serve as engineer of record on. And Chance has been teaching the Level 3 class for several years now. So Chance will be teaching tomorrow and Thursday, and I will be back with you on Wednesday. So just a quick overview of how the course will be laid out. We will take a 15-minute break kind of in the middle of each session for the next 4 sessions. Also, we'll be pausing periodically to see if there's any questions that have been typed in. And if I don't pause, then Lauren, feel free to just jump in and interrupt if there's several questions that have kind of built up. Today, we'll be looking at just an introduction to the PCI certification programs, and then Chapter 1 and Chapter 2 of the Level 3 material. Tomorrow, we'll be looking at Chapters 3 and 4 and the first half of Chapter 5. And then on Wednesday, we'll be finishing up Chapter 5 and then looking at alternative testing for concrete and deflected pre-stressing strands. And then we'll wrap things up on Thursday with Chapters 8 and 9, product control and welding. So that's what the class is going to look like over the next few days. As far as course materials are concerned, I believe you should have gotten a link to the presentation slides, as well as the supplementary practice problems that are included as part of this course. So just as a reminder, there are problems at the end of each chapter in your TM103 textbook. In addition to those practice problems, there are also some supplementary practice problems that PCI provides. You should also have a copy of your TM103 with you. If you don't have it there in front of you, over the next few minutes while we're talking about certification programs, grab your physical copy of the textbook because it will come in handy as we go through the class. The best study aid that I can recommend to you is your book. And so the topics that we discuss during the class, if instead of taking notes on those things, instead you just highlight or underline those items in your book, then you have a very good study guide for the certification exam that you will be eligible for after completing the class. There is a new version of TM103 that is in the works. The content has been reviewed, so it's in the final stages of editing and preparation for publishing. Don't have a date yet, unless Lauren has a date, but last I heard there was not a date yet for when that manual will be released, but it is in the works, and so hopefully before too long we'll have new TM103 manuals available. All right, let's do just a quick overview of the PCI certification programs. Before we get into the programs, let's talk a little bit about quality control and what we mean by quality control and quality assurance. So oftentimes these two terms, quality control and quality assurance, are used interchangeably, and to a certain extent that is okay. but there are some subtle differences between the two. Quality control are the actual activities that we use to ensure that products are manufactured in accordance with the specified requirements. So quality control is the actual physical things that we do as part of the quality assurance process. Quality assurance is just that, it's a process. It's a system of knowledge, programs, activities, all of these things that are listed on your screen. So it's the big picture. It's how we go about ensuring that products are manufactured in accordance with industry and job-specific requirements. Okay, so oftentimes used interchangeably, but there is a subtle difference. Quality control is the actual activities that we use. Quality assurance is the big picture system that oversees that quality control process. Certification is a program that is implemented to check whether or not a quality system is functioning as it is intended to function. So the certification helps to ensure that the standards are clearly communicated, what is expected, and it helps to ensure that the quality system is meeting those standards and that it is functioning in accordance with those standard requirements. And so the ultimate goal here is to increase our probability of a successful project. We want to have a greater level of confidence that the products that we manufacture actually do meet the job-specific and industry-specific requirements. All right, so with that in mind, PCI has 3 different certification programs. The first is the Plant Certification Program, which started in 1967. As Lauren mentioned, when PCI started the Plant Certification Program, they partnered with Ross Bryan Associates to implement that program, and we've been partnering with PCI ever since then. We also have the Personnel Certification Program, which started in 1985, and then the Field Certification Program, which started in 1999. So we'll talk about each of these in a little bit more detail, just so you have a better understanding of how each of these works. So the Plant Certification Program allows plants to be certified in several different groups and categories. So if the plant is an architectural producer, they can be certified either AA, AB, AC, AD, or AT. So AT is architectural products that are smaller, modular. We refer to this as architectural trim. This would be window sills, coping units, door surrounds, those sorts of smaller precast elements. AA through AD is intended to cover larger architectural precast elements such as building panels. The difference between AA, AB, AC, and AD is not related to the quality of the panel. The quality of the finish is expected to be the same no matter what category the plant is certified in. Rather, the differences between these categories is the level of complexity that the plant is capable of achieving. So AA is the highest level of complexity. These are panels that have pretty significant deviations in the formwork, may incorporate multiple finishes within a given panel, and may incorporate multiple mixes within a given panel. So that would be the most complex architectural precast that is used. And then on the other end of the spectrum would be AD. AD would be more simple architectural precast, such as just a flat panel, maybe some reveals, single concrete mix, a single finish within the panel. And so then there's varying degrees of complexity between those two extremes, and those are covered by AB and AC. In addition to architectural precast certification, we also have bridge, commercial, and glass fiber reinforced concrete certification. So bridge products are products that are primarily manufactured for a governing agency, such as a DOT, and they include bridge girders, piles, pile caps, any type of element that you would see used in mass public service projects that are above ground. PCI typically does not include utility type products such as culverts. Actually, they do cover culverts because that's a bridge product, but elements like manholes or precast concrete pipe, that would not be covered by PCI under this category of bridge products. Commercial products are elements like beams, columns, wall panels, hollow core, any precast element that would be used as part of the superstructure or cladding on a commercial type structure would fall under Group C. And then glass fiber reinforced concrete is something that some of you may not be very familiar with. There are not a whole lot of producers of GFRC across the country. Basically, GFRC is a thin shell precast architectural unit. The advantage to using glass fiber reinforced concrete is that the unit weight of the precast panel is less than normal architectural precast because, again, it is a thin shell of glass fiber reinforced concrete. And so there can be significant weight savings by using GFRC. So we oftentimes see GFRC used for architectural applications in areas where there might be a high risk of seismic loading. The seismic load on a structure is directly related to the weight of the structure. So anything that can be done to reduce the weight of the structure helps to reduce the seismic load. So we see glass fiber reinforced concrete used a lot on the West Coast and in other high seismic areas. It can also be used in high density areas such as urban centers where we don't really have the space to get a large crane to lift heavier precast elements. We can only use a smaller crane, and so we need to reduce the weight of the elements that are being lifted by that crane. So we see a lot of glass fiber reinforced concrete used in New York City and other really dense urban areas, just so that the contractor can use a smaller, lower capacity crane. All right, our commercial and bridge categories of certification are numbered. A plant can be certified B1 through B4 or C1 through C4. And what those numbers represent is the level of complexity in the pre-stressing. So a C1 or a B1 product would be non-pre-stressed, precast only. A B2 or C2 product would be pre-stressed, but it would be a fairly simple pre-stressed element that is repetitively cast. Some examples of this would be hollow core, piles, or deck slabs. B3 or C3 would be pre-stressed elements that are more complex or are flexural elements such as beams. Double T's, bridge girders would fall under this category. And then B4 or C4 would be flexural products that have deflected pre-stressing strands. So a drape strand girder, deflected strand double T would fall under B4 or C4 category. The manuals that are used to govern the certification program are MNL 116 for bridge and commercial, MNL 117 for architectural, and MNL 130 for glass fiber reinforced concrete. All right, so that's the plant certification program. Next, we have the personnel certification program. Personnel certification is divided into 3 different categories. Level 1 certification is required for plants that do not pre-stress concrete. So PCI requires that if the plant does not do any pre-stressing, they have at least one person who is PCI Level 1 certified at the plant. If the plant does pre-stressing, then PCI requires that the plant have at least one person who is PCI Level 2 certified. Now, most plants go well above and beyond this requirement. They have multiple people on staff that are PCI certified. The key difference between PCI Level 1 and Level 2 is that Level 2 incorporates pre-stressing, whereas Level 1 does not. So the curriculum for Level 1 covers basic quality control program requirements. talks about concrete and curing, materials, reinforcement, what the requirements are for those raw materials. We get into the basics of reading shop drawings and also talk a little bit about welding. Level 2 takes that level 1 material and adds more information to that. It also adds then pre-stressing of strands. And then level 3 is more advanced. We cover some of the elements that are covered in level 1 and level 2, adding more information to those, but we also introduce some new material in level 3. We get into a deeper discussion on cement chemistry, what the different aspects, the different oxides in the cement do. We also talk about concrete mix design development. We'll spend a good bit of time tomorrow afternoon and then on Wednesday as well, going through chapter 5 and talking about concrete mix design development. We also talk about some alternative ways that we can test and evaluate the quality of concrete. And we touch on pre-stressing, just do a general review of what you learned in level 2, but then we add to that drape strand pre-stressing. So that's kind of the big picture of PCI level 3. All right, and then we also have the field certification program. Don't really have any additional detail in this presentation for that, but it's also referred to as a rector certification. PCI has a personnel training school for field auditors as well as company auditors, and that program is really growing. It seems like every year we have more and more erectors who are getting certified under that program. A few years ago, the program moved to an independent third-party certification evaluation. So PCI now has auditors that evaluate the erector certification program participants, do that on an annual basis, and then send those reports in to PCI. Initially, the erector certification program was more of a self-auditing or shared auditing program, but it is now independently audited. So that program is really taken off. All right, so that's just the big picture overview of the certification programs that are offered by PCI. So without any further delay, we'll go ahead and jump into the level 3 class, what everybody is here for. And as I mentioned, you should have your TM103 manual. That's the best way of taking notes and keeping track of what the key pieces of information are for the class. So I would definitely encourage you to have your book in front of you. We will be going through the book from chapter 1 through chapter 9. We do this a little bit differently than we do level 1 and level 2. Level 1 and level 2 are a little bit more topic centered, and so you may do a little bit of jumping around in the TM101 manual as part of the school. The level 3 school, we do differently. We literally take the TM103 manual, which is that's what defines the body of knowledge for level 3 certification. So we take that manual and we just step through the manual chapter by chapter, talking about the information that is trying to be communicated. As we go along, I'll give you some examples of just things that I've seen over the years that relates to different topics that will hopefully help you to understand what is being communicated, and will also maybe give you the opportunity to kind of tuck that away in your mind in a way that will be more easily retrieved when you need it for either the exam or just in general practice within the industry as you advance in your career. All right, so first thing we're going to do is start with chapter 1. We'll be covering chapter 1 and chapter 2 today. We will stop for a 15-minute break between the two chapters. So without any further ado, we'll get going with chapter 1, talking about the properties of concrete components. So when we talk about what is in concrete, those different materials are what we're going to be doing in a big picture take on, both in chapter 1 and then also in in chapter 2 to a certain extent. So as far as the overview for chapter 1, we're first going to talk about cement. One of the key things that we're going to discuss when talking about cement is the water-cement ratio. You'll see water-cement ratio come up many, many times over the course of the next few days. It's not just in chapter 1 and chapter 2, but in most of the other chapters, water-cement ratio will come up at some point in time. Next, we'll talk about aggregates. We'll talk about fine, coarse, and lightweight aggregates. We'll talk about what divides fine aggregates from coarse aggregates. And we'll talk about admixtures. We'll focus on the different types of admixtures that we most commonly see used in precast operations. So we'll touch on each of those admixtures, talk about how that admixture does its work, how admixtures interreact with each other, and some things to keep in mind with regard to the general use of admixtures. All right, so that's the three main parts of the chapter for chapter 1 that we'll be looking at today. So let's dive in and start talking about cement. So the components for cement are primarily calcium oxide, silicon dioxide, and aluminum oxide. And so the sources of those oxides can vary, but the most common sources are limestone for the calcium oxide, and then clay or shale for the silicon dioxide and aluminum oxide. So those are the three primary oxides, and we're going to take these naturally occurring materials, limestone, clay, and shale, and some other materials as well, and blend them together in the cement production process, so that we go from these raw materials on one end of the process to this fine powder that we know as Portland cement at the other end of the process. So the production process, just a schematic overview of that, is shown there on your screen. So we start with our raw materials there at the top of the slide, our limestone, our clay and shale, and our other raw materials that contribute to the oxide content of our cement. So we grind those materials down and we proportion those based on the particular design that is being used for the Portland cement. Grind those materials down and we blend them in proportion. And then we run that blended material through a kiln. Heat up that material such that it combines chemically with each other. What we get out of the kiln is an ugly looking mass of a material that's referred to as clinker. So that's not our cement. We're not quite to the point of cement yet, but we get this these gobs of material that are referred to as clinker. And so then we have to take that clinker and we have to grind it down into the material that we refer to as cement. As part of that process of taking the clinker and grinding it down, we may introduce some gypsum into the mixture at that point. Gypsum helps to control the set time of our cement, so the amount of gypsum that is added will depend on the proportion of the other materials that are going into our cement. But the clinker, the gypsum, goes through a final grinding process, and the material is ground down to a fineness that is suitable for the particular type of cement that is being produced. And then that fine powdery material is what we recognize as Portland cement, and it goes into storage silos from which the cement manufacturer will then ship to the various users of the cement, whether it be precast plants, whether it be ready mix plants, whether it be other manufacturers who use Portland cement. So that's kind of the big picture process for manufacturing cement. All right, one of the key properties that we're going to be looking at as we combine cement with other materials to produce our concrete is we're going to be looking at the water-cement ratio. So this is the name of the ratio tells us how we go about calculating the ratio. We take the amount of water that is available for mixing, for interacting with the cement, divide that by the amount of cement in our mix, and that gives us a ratio that we refer to as the water-cement ratio. Now in your book it mentions that we need a minimum of 4 ounces of water to fully hydrate a pound of cement. And so what that means is that we need a minimum water cement ratio of 0.25. If we have a water cement ratio of less than 0.25, then we don't have enough moisture available to interact with the cement to fully hydrate that cement. Now I'm using that term hydrate the cement. So keep in mind that when we combine water and cement, that it is a chemical reaction that is taking place. That's why we do not refer to as concrete as it goes from the plastic state to the hardened state as drying. We refer to it as curing because it isn't just a drying process. It is a chemical reaction that's taking place between the water and the cement to form this hardened material that we refer to as concrete. Okay, so we have a minimum water cement ratio of 0.25. The water cement ratio can go up from there. For cast in place applications, it's not uncommon to have water cement ratios of 0.5 or even greater, 0.55, 0.6 possibly for some lower strength elements. But typically in precast and pre-stressed concrete, we're working with a higher quality concrete than just a general run-of-the-mill cast in place mix. And so generally you're going to see in precast and pre-stressed operations that the water cement ratio generally maxes out at around 0.40 to 0.45. It would be unusual to see a mix in a precast plant that has a required water cement ratio greater than 0.45. Anymore, it's fairly uncommon to see one with a water cement ratio greater than 0.40. So generally, we're going to be looking at water cement ratios between 0.25 and 0.40. Now, on that 0.25 end of the spectrum, keep in mind that that is the minimum amount of water needed to react with the cement. Now, we know that we don't work in a perfect world. We're always going to have some losses that take place. We're going to lose moisture to the atmosphere. There is going to be some evaporation that takes place during the mixing, transporting and placing of the concrete. We may lose a little bit of mixture to dry form work. So there's other ways that we can lose some moisture as well. So given that we are going to be losing some moisture, generally we want to have a water cement ratio that is a little bit above 0.25 as our starting place. So even with zero slump mixes like that are used with Holocore, oftentimes we see a water cement ratio in the 0.28 to 0.31 range. So even for a zero slump mix, we're going to have a water cement ratio greater than 0.25. All right, so we have an example calculation there in your book that shows calculating water cement ratio if you need to convert from gallons and sacks of cement, that it is just the water weight in pounds divided by the cement weight in pounds, gives you your water cement ratio. So how does water cement ratio really affect the performance of your mix? Well, figure 1.1 on page 1.3 in your book is there just to highlight for you how water cement ratio will affect the performance of your concrete mix. So in part A of this figure, we have several different samples. What's represented there is the water cement ratio of those samples. So we have the same amount of cement that's represented by the bottom portion of each of those bar graphs. And then we have varying amounts of water. And so that's why each column is a little bit taller than the one to the left of it. So as our water cement ratio goes up, we're using more water in our mix design. And so the volume of the water cement ratio is represented there by these columns. So after each of these samples are cured, they've fully reacted and any excess water has been removed. When we weigh those samples, what we should find is that they weigh the same. So even though we started out with varying amounts of water, since we started out with the same amount of cement for each sample, that same amount of cement will react with the same amount of water, and so we end up with a sample that weighs the same. But since we started with more material because we had more water, the volume of these different samples will be a little bit different. The samples with higher water cement ratios will be a little bit larger than the samples with the lower water cement ratios. So even though they all weigh the same, they do not all occupy the same volume. So if you have a sample of material that was at a water cement ratio of 0.25 and a sample of material that was at a water cement ratio of 0.70, those two samples, they weigh the same. That's what figure B is showing you there. But the sample with the higher water cement ratio is going to be larger. So if you've got two samples of material and they weigh the same, but one sample is larger than the other, then what that tells you is that the larger sample is less dense. If it's less dense, that means that there's more space between the particles within the sample. And so that's exactly what happens with our concrete. As water cement ratio goes up, we have more space between the hydrated cement grains within our cured concrete. And so that means we have more of a lattice type structure than a dense type structure, a solid type structure. And so what figure C is showing us there is that the denser structure with the lower water cement ratio is going to have a higher compressive strength. So that's one of the key drawbacks to using a high water cement ratio, is that we lose concrete strength, we lose compressive strength in those samples. And another issue that I just alluded to is that the higher your water cement ratio, the more lattice-like the structure within the concrete. So that means that there's more space within the concrete that can be occupied by other things, such as water and air. And so not only does that make the concrete weaker, but it also makes the concrete less durable. It's more susceptible to water freezing and causing damage. It's also more susceptible to penetration by other liquids such as sulfates, acids, chlorides, anything that the concrete comes in contact with in its environment. It's going to be more susceptible to absorbing that adverse material, which could negatively affect the durability of the concrete over a long period of time. Okay, so we want to make sure that we keep our water cement ratio as low as we can based on the needs of the concrete, what type of product the concrete is going to be used in, and how that product is then going to be used in service. All right, and this figure just runs through some of the highlights of figure 1.1 that we just discussed. All right, so let's talk a little bit about aggregates. So we're accustomed to discussing coarse aggregates and fine aggregates, but you may have never really thought about, well, technically, what's the dividing line? We know that coarse aggregates are bigger particles. We know that fine aggregates are smaller particles, but technically, what is the definition of a coarse aggregate versus a fine aggregate? Well, the answer to that question is the number 4 sieve. So any particles that are retained on the number 4 sieve or above would be considered coarse aggregate particles. Anything that passes the number 4 sieve would be considered a fine aggregate particle. All right, so if we have a material that the great majority of the particles within that material are retained on or above the number 4 sieve, then we would classify that as a coarse aggregate. If we have another material that the majority of the particles in that material pass the number 4 sieve, then we would refer to that as a fine aggregate. So let's talk about these two classifications in a little bit more detail. First off, fine aggregates can be derived in a couple of different ways. We can have naturally occurring fine aggregates, such as sands that are dredged from a river bottom or from some other geological formation. Or we can have a manufactured sand. A manufactured sand is when we take a coarse aggregate and we crush it down until the particles are small enough that we can call it a fine aggregate. All right, so we can either have fine aggregates that naturally occur, nature has done the crushing for us, or we can manufacture sands where we actually crush coarse aggregates down into fine aggregate sizes. Right? Typically, the finer the aggregate material, the more water demand we will have in our mix design. So we use an example of this in level 1 and level 2. So you may have seen this example before, but this is our unit cube. And on the left, we have a solid cube there that has a volume of 1 cubic inch. So we'll call this a nice, perfectly square chunk of aggregate, 1 inch on each side. So it has a volume of 1 cubic inch, and it has a surface area of 6 square inches. Now, if we subdivide that aggregate particle in all 3 dimensions, then we end up with the next figure there. We still have a volume of 1 cubic inch of material, but we've essentially doubled the surface area of the aggregate, and we now have 12 square inches. All right, if we subdivide each of those particles in all 3 dimensions, then we end up with the third figure. We still have 1 cubic inch of material, but now we have a surface area of 24 square inches. So our surface area has quadrupled, and we're just now getting to the dividing line between coarse aggregate and fine aggregate. Each of those aggregate particles is about 1/4 of an inch, which that's the dividing line, that number 4 sieve. So we would have to subdivide these particles yet again just to get through the doorway of a fine aggregate. So the purpose of this figure is just to highlight to you that the finer a material gets, the more surface area that we have to coat with our cement and water paste. And it's not just a slight increase in surface area, it's a multiple increase in surface area. All right, so the gradation of our fine aggregate is very important to us because a big part of that gradation is the surface area, and that dictates how much water and cement slurry we need to coat the aggregate particles. So if there's variation in the gradation of our fine aggregate, that can cause problems if the gradation becomes coarser. Then we may have excess water in our mix, which can lead to bleeding. The formation of water on the surface of the concrete, the placed concrete. If the gradation of our fine aggregate gets finer, then that can lead to a tightening up of our mix, a loss of workability, a loss of slump, because now we have more surface area that has to be coated by our cement and water slurry. All right, so the gradation of our aggregates, because it can have such a significant effect on the workability of the concrete, can also affect the durability. If a mix tightens up, one of the first things that we sometimes do is just add a little bit more water. But when we add a little bit more water, we're increasing our water cement ratio, which is adversely affecting the durability of our concrete. So if we do need to increase the water because the gradation of our sand has gotten finer, then we also need to increase the cement content so that we are maintaining the same water cement ratio. Another important material property for fine aggregates is that they should be inert in the sense that they do not react chemically with the oxides that are present in the cement. So generally it is the potassium and the sodium oxides in the cement that tend to react most commonly with our aggregates. And so there are a variety of ASTM tests that can be conducted to determine just how reactive an aggregate source is. Ideally, we want to use aggregates that have been tested and show that they are not reactive with the potassium and the sodium oxides that are present in the cement. All right, next, let's talk a little bit about coarse aggregates. The primary material property that we are concerned with when it comes to coarse aggregates is the maximum size of the aggregate particles and the uniformity of the gradation from batch to batch. So we're concerned about the maximum size of the aggregate particles because that comes into play with regard to how well the concrete is able to get around reinforcing bars, fit between reinforcing bars and the side forms. So the maximum size of the aggregate can be a limiting factor on the design of the precast unit if we're using an aggregate that is relatively large in size. Another thing that we're concerned with is the uniformity of the gradation from batch to batch. Now, the coarse aggregate effect of variation in gradation is not as significant as far as how that effect shows up in the performance of our concrete mix. A concrete mix is very sensitive to changes in gradation of the sand, but not as sensitive to changes in the gradation of the coarse aggregate. So as far as what the gradation of the coarse aggregate is, we're not as concerned with, but we do want to make sure that whatever that gradation is, that it is consistent from batch to batch so that we don't get slight variations, so that we know that our mix design is functioning as we intended for it to function. As far as the shape of the coarse aggregate is concerned, we didn't really discuss particle shape talking about fine aggregates because it really doesn't come into play as much as it does with coarse aggregates. Generally, we want to avoid coarse aggregates that have flat, slivery shapes, very rough textures. Now, obviously, if it is a crushed aggregate, it's going to have a rough texture, but even then, we want to avoid aggregate particles that have a flat shape or a very irregular shape, because that can lead to a very harsh concrete mixture that does not perform well with regard to slump and workability. Generally, the rougher the texture of the coarse aggregate, then the more fine aggregate we're going to need to get to a workable mix. The more fine aggregate that we use, the more surface area we have to coat, and so that means the more cement and water that's going to be needed in order to get a mix that is functioning the way that we want it to function. Anytime that we're adding cement to our mix, then that increases the cost. So ideally, we want to have well-textured aggregates that interact and interlock with each other over a smooth gradation curve. That will help to minimize the amount of cement that we need to use in order to achieve the desired level of concrete strength. Sometimes we use coarse aggregates that do not have a nice smooth gradation curve. We refer to these as gap graded aggregates. So these gap graded aggregates generally will not conform to ASTM C33 gradation requirements. Conformance to ASTM C33 is a common specification requirement, but to achieve the aesthetics that are desired for an architectural precast unit, sometimes we may have to use an aggregate that does not meet C33 gradation requirements. Generally, that's going to be okay. We can still come up with a concrete mix design that is going to perform adequately. It's going to meet the strength requirements. It's going to have a level of workability that is acceptable for placing the concrete and getting it finished in accordance with the project specification requirements. So generally, it's not a huge deal if we have to use a gap-graded architectural aggregate. But one thing to keep in mind is that if the project specification explicitly requires ASTM C33 gradation conformance, then if we're having to use an aggregate that does not meet C33 gradation requirements, then we need to let the specifier know that. So generally, that's going to be either the architect or the engineer for the project. Generally, it's not going to be too big of a concern to them if you assure them that even though you're having to use a gap-graded aggregate, that you'll still be able to get the desired strength and aesthetic performance out of the mix. But it is something that since you are not meeting a specified requirement, you need to notify the specifier that that requirement is not being met and get their approval to proceed. All right, another thing to keep in mind to investigate with regard to coarse aggregates is the soundness of the aggregate. So we have ASTM C88, which measures the magnesium sulfate soundness loss of the aggregate. To be a good quality aggregate, that magnesium sulfate soundness loss should be less than 8%. So this is another one of those tests, qualifying tests that should be done, not necessarily by the plant, but by the aggregate supplier and reported to the plant so that the plant can evaluate the quality of the aggregate in making the determination as to whether or not to use, in making the determination of whether or not to use the aggregate. Just like we want our fine aggregates to be inert, we also want the coarse aggregate to be inert. We want to use an aggregate that does not react with the sodium and potassium oxides in the cement. So there are a variety of ASTM tests that can be used to evaluate coarse aggregates, just like we can evaluate fine aggregates. One way that we can offset the potential for that alkali reactivity is to use a low alkali cement. To qualify as low alkali, a cement has to have a sodium and potassium oxide equivalent of less than 0.60%. So generally, these two materials have different molecular weights, and so we normalize the potassium molecular weight to the sodium molecular weight, and so it's reported as a Na2O, or sodium oxide equivalent. So as long as that sodium oxide equivalent is less than 0.60%, then the cement can be classified as a low alkali cement. All right, so if you have an aggregate that is potentially reactive, this is one step that you can take to help mitigate that risk of reactivity. Ideally, you would just not use the potentially reactive aggregate. Sometimes that's not an option. You have to use a potentially reactive aggregate. And so in those cases, definitely a low alkali cement should be used. All right, so that is coarse aggregates and fine aggregate. Now let's talk a little bit about lightweight aggregates. Lightweight aggregates are generally derived from naturally occurring aggregates such as shale, clay, or slate. They are manufactured from these raw materials. The manufacturing process is similar to the way you would pop corn. Just like you put a small corn kernel in hot oil, it rapidly expands and puffs up into the popcorn that we would eat. For lightweight aggregates that are expanded shale, clay, or slate, smaller aggregate particles are submerged in water. They are then heated rapidly, such that the water that is caught within the aggregate particle vaporizes more quickly than it can make its way out of the aggregate particle. And as a result, the aggregate particle gets puffed up. And so that's how we get our lightweight aggregates. So that's manufactured lightweight aggregates. We also have naturally occurring lightweight aggregates such as scoria, pumice. Those can also be used as lightweight aggregate, but the most common types of lightweight aggregate we see used in precast plants are the manufactured lightweight aggregates that are derived from expanding shale, clay, or slate. These materials are covered by ASTM C330. As far as mixed designs are concerned at a precast plant, we can have an all lightweight mixed design, which means that we're using lightweight sand and lightweight coarse aggregate. Or we can have a sand lightweight mixed design or semi-lightweight mixed design, which incorporates regular weight sand with a lightweight coarse aggregate. The sand lightweight is the most common type of lightweight mixed design we see used in precast plants. These lightweight aggregates are difficult to work with. They do complicate the manufacturing and the quality control process. So we can use a lightweight coarse aggregate and still get a significant reduction in the unit weight of our concrete mix, but use a normal weight sand. Using a lightweight sand is even more complicated than using a lightweight coarse aggregate. And so just to minimize the complexity and the difficulty, a lot of plants elect to use a regular weight sand and then a lightweight coarse aggregate if they need to develop a lightweight concrete mix. One of the key complicating factors when using a lightweight aggregate is the water absorption. For a regular weight aggregate, you may be looking at an absorption of 1 to 2%, somewhere in that range, just depending on the density of the aggregate. But for a lightweight aggregate, you may be looking at a water absorption of 25 to 30%. It's significantly higher. It's a multiple higher. And so because the water content of the aggregate can vary so widely, it really complicates the batching process because we're not able to achieve the same level of consistency with moisture content that we are with a regular weight aggregate. So complicating things further is that the specific gravity of the material is going to vary with the moisture content. Specific gravity variation with a regular weight aggregate is there, but it's nowhere near as significant as it is with a lightweight aggregate, just due to the high potential moisture content. We'll talk a little bit more about specific gravity and specific gravity of aggregates and how that affects our concrete mix design tomorrow at the end of the day, and then on Wednesday we'll start talking about mixed designs. We'll finish up talking about mixed designs on Wednesday, and so we'll talk a lot about specific gravity once we get into Chapter 5. All right, quality control is also complicated a little bit when we're using lightweight aggregates. For a regular weight concrete mix, PCI requires that we evaluate the fresh concrete unit weight a minimum of once per week. Most plants evaluate unit weight more frequently than that, but the minimum requirement is once per week. Now, if it's a lightweight mix, we have to evaluate that fresh concrete unit weight on a daily basis. All right, so a little bit more quality control testing is required for lightweight concrete. Also, the test method that's required is different. Most plants will use a pressure meter to evaluate air content in a mix, but if it's a lightweight mix, we can't use the pressure meter. We have to use the rollometer, which is a little bit more involved, usually takes a little bit longer. It's a little bit more complicated test to perform. All right, so our quality control, we're going to do testing more frequently, and the test method that we're going to use is a little more complicated than the test method that maybe we would use with a normal weight aggregate. So those are some things just to keep in mind when you are dealing with a lightweight concrete mix design at a plant. All right, now let's transition from talking about aggregates to talking about admixtures. We're going to discuss each of these different admixtures that are listed on your screen in detail. These are the most common admixtures that we see used in precast operations. Now notice that there are some things included in this list that sometimes do not get included as an admixture. So one thing is pozzolans and microsilica. Generally, we would consider pozzolans and microsilica to be a cementitious material, and so we would classify those along with our cement as supplementary cementitious materials. But for whatever reason, when TM 103 was written, they decided to include those materials under admixtures. I think with the new TM 103, they're going to separate those back out and include the discussion of pozzolans and microsilica with cement. But for now, they're included in the admixture section. Also included in the admixture section is pigments. So this makes a little bit more sense to be included as an admixture. But oftentimes, day in, day out, we don't really think of pigments as admixtures. We think of them as kind of a separate category of additive that would be potentially used in architectural precast. But as far as the TM 103 discussion is concerned, we're going to include pigments in the discussion of admixtures. All right, so the first admixture we're going to discuss is air entraining admixtures. These are covered by ASTM C260. The way these admixtures work is they introduce microscopic bubbles into the matrix of our concrete mix. Those bubbles then provide space for expansion of freezing water. So air entraining is very effective in helping to minimize the amount of damage that occurs due to freeze-thaw cycles. As a result of that, we see air entraining specified more commonly in areas where, due to the environment, the concrete is going to see a higher number of freeze-thaw cycles. So we don't see a whole lot of air entraining used in southern parts of the U.S., where there are very few, if any, freeze-thaw cycles. We definitely see it used a lot more in the middle part of the U.S. And then in northern regions as well. So keep in mind that the way these air entraining admixtures work by making these microscopic air bubbles is it's not a chemical reaction that's taking place. It's purely a mechanical reaction. It's very similar to if you put liquid soap on your hands and then started rubbing your hands and you get this generation of foam. That's analogous to what's happening in your concrete when you put a liquid air entraining admixture in. Once that liquid air entraining admixture is exposed to the mechanical injury or the mechanical energy of the mixing process, then it starts producing these microscopic bubbles which get distributed throughout the matrix of the concrete mix. All right, so the key component of the air entrainment is the mixing process, putting the admixture in during the mixing process. If we put some air entraining admixture into a concrete that had already been mixed, then it really wouldn't do anything as far as causing air entrainment to occur within that mix. All right, so the key reason we would use an air entraining admixture is to improve the performance of the concrete under freeze-thaw conditions, but there are also some other advantages to using air entraining admixtures. They enhance the cohesion of the components of the concrete, which improves the workability. So we can improve the workability without significantly reducing the strength, although we do see a strength reduction. Not necessarily as much strength reduction as we would see by adding water, but we do see a bit of strength reduction, and we'll see that on the next slide. We'll see the comparison of the increase in durability and the decrease in the compressive strength. Keep in mind that very fine material in your sand, and when I say very fine material, I mean material finer than the number 100 sieve, that can affect the formation of these microscopic air bubbles within the matrix of the concrete. So if you're using a coarse aggregate that is dusty or a fine aggregate that has a very fine gradation, then you may end up having to use more air entraining admixture than you would otherwise need to use just in order to achieve the desired level of air entrainment. The temperature of the concrete mix generally inversely affects the air content. So as temperature goes up, you're going to get less benefit from your air entraining admixture. So if a plant has a standard mix that they use throughout the year, that's an air entrained mix, what they may find is that in the summer months, they have to use more air entraining admixture in order to achieve the desired level of air entrainment. So as fresh concrete temperature goes up, the effectiveness of the air entraining admixture goes down. All right, there's also a relationship between air content and slump. Generally, as air content goes up, we're going to get a little bit more workability as well. So if you're a little bit low on your slump, but you're also low on your air entraining level of air entrainment, then you may want to try adjusting your air content to get it into the range where you want it, and then reevaluate your slump, because just by increasing the air content, you may get an additional amount of workability that meets your requirement without having to actually increase your water cement ratio or the amount of water reducer that you're using. All right, so let's talk a little bit about how air entrainment affects the compressive strength and the durability of the concrete. So shown here is a graph that illustrates how air entrainment helps to improve the durability of the concrete, helps to improve the freeze-thaw resistance of the concrete. But notice that that improvement in durability does have a peak. At around 7% air content, you get a peak in durability, and if you keep increasing air content beyond that point, then you actually get a loss in durability. All right, so we get a peak in durability using air content of around 7%. Now notice the compressive strength. As air content goes up, we get a linear decrease in the compressive strength of the concrete. So the more air entrainment we use, the more adversely, negatively affected the strength of the concrete is going to be. So for these two reasons, what we generally want to do is use a water cement ratio that is right in the middle of where we want it to be. We don't want to exceed the amount of water that's needed. We want to keep a low water cement ratio. But once we've got that water cement ratio dialed in and we're looking at our air entrainment, we also want to keep that on the low side of our target value because we can increase our durability and minimize the amount of compressive strength that's being lost. So as an example, if I know my durability is going to peak around 7%, then between 4% and 10% air content, I'm essentially going to have the same level of durability. But I'm going to have a much better compressive strength at 4% air than I'm going to have at 10% air. And so for that reason, I'm going to stay on the low side of that air content range. So instead of using an air content of 4 to 10, I'm going to say my target air content is 4 to 7. So that way I'm getting the same level of durability that I would with an air content range of 4 to 10, but I'm getting better strength on average than I would if I was using an air content of 4 to 10. Because I'm staying higher up on that compressive strength curve by limiting my air content to a maximum of 7, keeping it between 4 and 7. All right, so that's a very common specification for air content, 5.5% plus or minus 1.5%. So that means our allowable air range is 4 to 7. That's a very common specified requirement for air content. And this graph shows you why. It's because we're getting that peak in durability, but we're minimizing the amount of compressive strength loss. All right, next we have water reducers. Water reducers reduce the amount of water that's required for a given consistency from 5 to 10%. So there are a few reasons why we might want to use a water reducer. One is to increase strength. If we reduce the amount of water while keeping our cement content the same, then we are effectively decreasing our water cement ratio, which should give us a higher strength mix. So that's one reason to use a water reducer. Another reason to use a water reducer is to get more workability without adding more water. So we can use a water reducer and then enhance our workability of the concrete mix without having to actually add water and increase our water cement ratio. Another reason we would use a water reducer is to economize the mix by reducing the amount of cement. We can take cement out of the mix and maintain our water cement ratio by using a water reducer. So that way we are producing our concrete for a lower cost because we've removed one of our high cost materials, some of one of our high cost materials, that being the cement. ASTMs which cover water reducers are type A and type D of ASTM C494. The difference between a type A and a type D water reducer is that a type D water reducer also has some retarding effects. So keep that in mind. If you're using a type D water reducer, there may be some delayed strength gain early on during initial curing. So just be prepared for that. In some instances, that may be to your advantage. If you're in a very hot environment and the concrete tends to kick off and start hardening very quickly, and you need a little bit more time to get the concrete properly finished, then using a type D water reducer may be to your advantage. On the other hand, if you're in an environment where you really want to get as much early strength as you can, then you may want to avoid using a type D water reducer and make sure that it is a type A so that you don't get any retarding effects. The retarding effects can be offset by using an accelerator. That's fine, but you are adding cost. So it may be more cost effective to just not use a type D water reducer, but to use a type A instead. Calcium chloride is a very effective accelerator, but we generally try to avoid adding any chlorides to our concrete mix, especially if it's a pre-stressed concrete element. We have a pretty strict limitation on the amount of chlorides that can be introduced into the mix. So if we are going to use an accelerator to offset the retarding effects of a type D water reducer, then you need to make sure that the accelerator that you're using is not introducing chlorides into your concrete. The state of the technology of admixtures is to the point where most admixture suppliers can produce very effective accelerators that do not incorporate calcium chloride. So this is not as big of a concern as it was in decades gone by, but it is still a good question to ask your admixture supplier just to make sure that the accelerator that you're using is a non-chloride accelerator. We'll talk a little bit more about chlorides in cement as we review additional chapters as well. Okay, next is retarders. So generally a retarder is going to be used in warmer weather to help slow down the initial set and the initial strength gain of the concrete. So we're going to retard that set and early strength gain so that we've got more time to get the concrete placed, consolidated, and finished properly. Retarders are covered by ASTM C494 Type B. Just like some water reducers have retarding effects, some retarders have water reducing effects. Generally, that's going to be to the plant's advantage if they're using a retarder that has some water reducing effects. Retarders may also entrain some air. So some trial batching probably needs to be done because you can quite possibly reduce the amount of air entraining admixture that you're using if you start incorporating a retarder into a mix. But trial batching is recommended so that you can evaluate what those effects are with your particular mix design. All right, the opposite of retarders are accelerators. Accelerators are typically used in cooler weather to help speed up the initial set and early strength gain of the concrete. So using an accelerator will help us to get the strength that we need for stripping so that we can turn the form over more frequently and have a more economical operation. So the way these work is they speed up the initial setting and strength gain of the oxides within the cement that contribute to early strength gain. So generally the C3S is going to be a primary contributor to the early strength gain of the concrete. The C2S also contributes, but not as much as the C3S. And so accelerators generally help to speed up the reaction of the C3S and C2S oxides. On the other hand, they generally slow down the reaction of the C3A and the C4AF. And we'll be talking about these oxide compounds in just a few minutes when we get into chapter 2. So these are referred to as Bogue compounds. And in chapter 2, we'll talk about how these oxides are calculated, how they're derived, and what these different oxides do as far as the physical performance of the cement. Accelerators can also cause color variation within the concrete, light and dark areas. So generally, you're not going to use an accelerator in any mix that aesthetics are a high priority. So if you do need to use an accelerator in a precast unit that aesthetics are important, then you definitely need to do some trial batching just to see what the effect that accelerator is going to be and whether that can be accommodated within the mix, within the project requirements. Again, the warning with regard to chlorides. Chlorides do make very good accelerators, but again, most admixture manufacturers can provide you with a very effective accelerator that does not incorporate additional chlorides. But it's a good question to ask. All right, next let's talk about high range water reducers. So high range water reducers were a huge advance in the concrete industry. Over the last 15 years or so, maybe upwards of 20, we've seen a big change in precast concrete that's resulted from the use of self-consolidating concrete. So 20 years prior to the introduction of self-consolidating concrete, we had the introduction of high-range water reducers. And this introduction of high-range water reducers was had just as big of an impact on precast manufacturing as the use of self-consolidating concrete has had. It was a huge advance for the time. High-range water reducers are covered by ASTM C494 and ASTM 1017. A water reducer, as we talked about a few minutes ago, can reduce the water demand by 5 to 10%, but a high-range water reducer can reduce the water demand by upwards of 30%. So much more significant reduction in the amount of water compared to just a regular water reducer. So we can end up with a mix that's a very low water cement content, but still has very good workability. So prior to the introduction of high-range water reducers, you may have had precast products that, because of strength requirements and water cement ratio, maybe the max those could be cast at was a 4-inch slump. And then after high-range water reducers, suddenly we could pour that same mix design, but at an 8-inch slump. So it's just a huge advancement in the manufacturing process. Significantly reduced the amount of labor that was required and the difficulty in that labor of placing the concrete and consolidating it, just a huge advance. Now keep in mind that there are also some drawbacks to using high-range water reducers. One of those is that the fresh concrete tends to be fairly sticky. And so if you have a finisher who is accustomed to working with non-plasticized mixes, and then they start having to finish a mix that does have a super plasticizer, they may complain a bit because it is definitely a stickier texture. They'll get used to it over time because the advantages to using high-range water reducer definitely outweigh the disadvantages. So another name for a high-range water reducer is a super plasticizer. So those two terms can be used interchangeably. High-range water reducer, super plasticizer, those refer to the same type of admixture. Another thing to be concerned with regard to using a high-range water reducer is what's referred to as pot life. So the pot life refers to the amount of time that the high-range water reducer actually has an effect on the concrete mix. Now, early generations of high-range water reducers had a fairly short pot life. And so what that meant is that you could start pouring a truck of concrete, and maybe it had an 8-inch slump when you started pouring, but then very quickly it lost slump and went back to that natural 4-inch slump. So definitely that could complicate the casting process. Over the years, admixture manufacturers have refined high-range water reducer chemistry such that they still have a pot life, but it's much broader. It lasts for a longer period of time, And once it starts wearing off, it doesn't wear off quickly. It's a more gradual wearing off, so that if you recognize that you're starting to lose slump because the high range water reducer is wearing off, then you've got more time to get the concrete out of the truck and get it placed and finished than maybe you would have 30 years ago, 40 years ago, when high range water reducers first started being used. All right, another big plus with using a high range water reducer is that you can get a high slump mix, but without the shrinkage that is oftentimes associated with high slump mixes if it's just based on water cement ratio. So as we discussed a few minutes ago, as water cement ratio goes up, that affects the volume of the concrete, and it also affects the shrinkage. So the higher the water cement ratio, generally the more shrinkage the concrete is going to see as the concrete cures. So you may have heard it said before that the largest a piece of concrete is going to be is at the time that it's poured, because it's only going to get smaller from that point. That is definitely true for just a regular Portland cement concrete mix. But that amount of shrinkage definitely is increased if the water cement ratio for the mix design is high. So by using a high range water reducer, we can keep our water cement ratio low, so we can get high workability, but without the shrinkage that is associated with high water cement ratio mixes. So I mentioned the troweling problems due to the texture of the fresh concrete being sticky. Another thing to keep in mind with a high range water reducer is that you may see an increase in bug holes on the surface of the concrete, and that results from just that sticky texture, the concrete sticking to the form and trapping small air bubbles on the surface of the form, which then leads to bug holes. So just some things to keep in mind when using a high range water reducer. Next is pozzolans. Pozzolans are natural materials that will, when combined with cement, will become cementitious. Generally, pozzolans in and of themselves are not cementitious. And so what that means is that you can mix a pozzolan with water and all you're going to get is mud. You're not really going to get something that will then transform into a hardened stone-like mass like Portland cement will when mixed with water. As a matter of fact, when I did my ACI testing initially, we walked into the lab to do the testing, and there in the middle of the lab was a big steel tray that had a pile of material in it under a tarp, and the instructor pulled the tarp off, and it was just a big lump of concrete. And I'm making air quotes because it looked like concrete, but it wasn't really concrete. It wasn't hardened into a stone-like mass. It was just like dried mud with rocks in it. And so the instructor grabs a shovel and he starts digging in this mass of material, digging out a hole in the middle of it. Then he got a bucket full of water, poured it in there, and kept mixing this material. And then eventually it looked like concrete. And so that's what we used to do our ACI testing. And then when we were finished, we dumped our samples back into this metal tray in the middle of the floor. And the instructor grabbed his shovel and he piled it up into a big pile, threw the tarp back over it, and we headed out. And so what this was, it was a quote unquote concrete mix that had no cement in it. It was 100% pozzolan, 100% fly ash. And so all it did was dry out. It never actually hydrated with the water. There was no cementitious reaction. So you're probably thinking, well, if fly ash doesn't become cementitious, if it doesn't react with the water, then why are we using it in our concrete? Well, fly ash has a very interesting property in that it does react with a substance called calcium hydroxide. And when it reacts with calcium hydroxide, it does become cementitious. Well, it just so happens that when cement and water chemically react with each other, we get a byproduct from that reaction called calcium hydroxide. So calcium hydroxide is naturally occurring in our concrete because of the reaction between the cement and the water. Once the fly ash then comes in contact with the calcium hydroxide, it becomes cementitious. It also starts reacting with the water, and then it does produce a hardened stone-like mass. It just takes it longer to do that. Because it takes it longer to do that, we get less heat that's generated from using fly ash. And so in some instances, that's an advantage. There may be certain applications where we don't want a lot of heat generated during the concrete curing process. But then for precast operations, generally we do want heat generated. We want that hardening process to move along at a fairly good rate so that we can gain our stripping strength and then turn the form over and pour it again the next day. All right, so one of the drawbacks to using a fly ash as a pozzolan is that we do get less early strength, and so we may not be able to turn our forms over quite as quickly as we would if we were not using the pozzolan. Another negative effect of using a pozzolan is that it is such a fine material that it can interfere with the production of entrained air. And so we may have to use more air entraining admixture in order to get the desired level of air entrainment than we would if the pozzolan was not used. So most common pozzolan that we see in use at precast plants is fly ash. Fly ash comes as a couple of different classes, Class C and Class F. The main difference between these two is that Class C fly ash does have some cementitious properties, not very many. It's not very cementitious, but it does have some cementitious reactivity that's available, whereas a Class F does not. So both of these react well with calcium hydroxide, but Class C does have some basic cementitious properties, and the Class F does not. One of the key material properties that we're interested in with regard to pozzolans is the loss on ignition. This is a test that can be conducted to determine the carbon content of the fly ash. Keep in mind that fly ash is a waste product. It results from the burning of coal. So depending on what type of coal is burned to get the fly ash, that will determine whether it's a Class C or a Class F ash. And then the loss on ignition test can be done to determine what the actual carbon content is of the fly ash. So the carbon content affects the air entrainment. There's also been some research that indicated that higher carbon contents decreased the durability of the concrete. But as more and more research has been done in this area, the consensus of the research seems to be that a well-designed mix using a high carbon content fly ash, you can still get a very durable mix. So that's good, especially in this day of carbon capture and trying to encapsulate as much carbon as we can into the concrete to reduce the amount of the carbon footprint of the cement manufacturing process. Since fly ash is a waste material, it will have variation in color. So generally you're not going to see fly ash used in products where aesthetics are important. Generally not going to see fly ash used in architectural precast because of this potential for color variation. Metakaolin is another pozzolan that we see used sometimes in precast, not nearly as commonly as fly ash. Metakaolin is a clay-based material. Just like with the fly ash, it's added as a dry powder. We probably see metakaolin, if you see it used, it's probably more commonly used in GFRC production. GFRC tends to have very high cement contents. That makes for a very strong material, but it also makes for a material that over the long term tends to become brittle and has a greater potential for cracking. It's not a very ductile material in the long term, but by using a material like metakaolin, that helps to increase the long-term ductility of the GFRC so that it does not become embrittled as quickly. Right, next is microsilica, or oftentimes referred to as silica fume. This is also a waste product. It comes from the manufacturing of silicon and ferrosilicon alloys. Microsilica is a very fine material, up to 100 times smaller than cement. So we're all familiar with how fine of a material cement is. Just imagine particles that are 100 times smaller than cement particles. So because it is such a fine material, it does have the capability of becoming airborne rather easily. Generally, it's not something that you want in the air as far as the air that you're breathing. So for that reason, we need to be careful with how microsilica is batched. Oftentimes, it will be batched from biodegradable pre-weighed bags. So the bags go into the mixer. That way the mixer can be closed and sealed before the bags are broken open, and the microsilica becomes airborne. It's contained to the mixer. It can also be batched as an emulsion in water. Mixed with water, it doesn't dissolve in water, but it can be emulsed in water. The key thing to keep in mind if you're using microsilica as an emulsion is that since it doesn't dissolve, it will settle out of the water. And so whatever container the emulsion is being stored in, that emulsion needs to be agitated. So it needs to have stirring paddles. It needs to have some way of agitating that material so that the silica fume doesn't settle out, so that we have a given proportion of silica fume throughout the volume of the water that it is suspended in. Generally, for silica fume, we can have a dosage of anywhere from 5 to 10%, or 5 to 15% of the cement content. So I think your book gives a little bit lower number than that. On page 1.13, there, the third paragraph down from the top, it says between 5 and 10%. We can see silica fume used at higher percentages. So I would change that to 15% because you can definitely use it above 10%. There are some drawbacks to using microsilica. It is such a fine material that it increases the surface area of the particles within your concrete to the point that it's very difficult to have enough water and cement slurry to coat all of the particles. And so the surface of the concrete tends to dry out quickly because you don't have much of any bleed water. So there's an increased potential for plastic shrinkage cracking when using silica fume. Also, there's an increase in potential for cracking the concrete during handling. Silica fume concrete, while it's very strong, while it's very dense, it does tend to be a little bit more brittle than regular concrete. So if you have a sharp edge, a sharp corner, then that corner may be more susceptible to spalling than it would if it was just a regular concrete mix design. So because of the potential for the concrete to dry out quickly and lead to plastic shrinkage cracking, water curing may need to be explored when using microsilica. So some other things to keep in mind when using microsilica are shown here on this slide. It does produce concrete that is darker in color. It's significantly darker than the cement, so it will be a darker colored concrete. The concrete does tend to be sticky. It's more difficult to work with in the plastic state. You have a greater potential for cracking during curing because of the rapid loss of moisture on the surface of the concrete and that minimal amount of bleed water that will be present. Generally, we want to finish the concrete as soon as we can after concrete placement so that we can get it covered and reduce the amount of moisture loss. You're probably going to need to use super plasticizers just to get to a level of workability that is manageable. You may need to use a retarder because silica fume mixes do tend to reach initial set pretty quick and then start gaining strength. So you may want to use a retarder just to slow down that process so that you have time to get the concrete placed, consolidated, and finished. Generally, high slump and silica fume do not go well together. The high slump is going to lead to a higher level of shrinkage and a greater potential for cracking. Usually a silica fume mix somewhere in the 3 to 5 inch slump range is going to be ideal. That's going to vary a little bit depending on the type of product that's being cast. But just as a general rule of thumb, if you would normally cast a given product at an 8 inch slump, then you may want to dial that down a little bit if you're using a silica fume mix just to help avoid some of these issues. All right, and the last admixture we're going to be talking about is corrosion inhibitor. As we all know, rusting reinforcing causes spalling. As steel rusts, that rust wants to occupy more volume than the original steel occupied, and so that leads to internal stresses within the concrete, which ultimately is going to end up with the concrete cracking and spalling. That's just going to allow more water and oxygen to get into the concrete, which is going to accelerate the rusting process. Another thing to keep in mind is that the concrete, to a certain extent, actually protects the reinforcing, not just in the sense that it provides space between the reinforcing and the environment, but also in the sense that the pH of the concrete tends to be high, and so that high pH allows for a thin oxide layer of corrosion on the reinforcing that is then protected. So as soon as you put the concrete around the reinforcing, you're going to get the formation of some oxide film on the surface of the reinforcing, but the high pH environment of the concrete helps to protect that oxide film, which then in and of itself helps to protect the reinforcing from further corrosion. Over time, the pH of the concrete environment goes down. It goes down naturally. It definitely is reduced in the presence of chlorides, such that we lose that protective thin oxide film on the reinforcing, and so the reinforcing becomes more susceptible to corrosion. In order to have corrosion, we need moisture and oxygen. So if we can keep moisture and oxygen off of the surface of the reinforcing, then that's going to go a long way towards minimizing corrosion. But since that corrosion wants to occupy more volume, it causes internal stresses in the concrete, ultimately leads to cracking and spalling, which then opens up the reinforcing to higher levels of moisture and oxygen, thus accelerating the corrosion process. You can see this sometimes in a structure. You may have a structure that has been in place for a number of years, never had any issues with corrosion, but then once the corrosion starts, you start seeing signs of corrosion. That corrosion is probably going to accelerate fairly quickly, and this is the reason why. Because as that corrosion advances, it opens up pathways for more moisture and oxygen to reach the reinforcing, which then speeds up the corrosion process. So it's just a vicious cycle once it starts, unless we do something to intervene and to cut off the source of moisture and oxygen and interfere with the corrosion process. All right, so as far as corrosion inhibitors are concerned, calcium nitrite is the most common that we see used. And what calcium nitrite does is it raises the chloride threshold level of the concrete. So it helps the concrete to protect the reinforcing from corrosion for a longer period of time. Now, keep in mind that corrosion inhibiting admixtures are used up over time. They are sacrificial. And so what that means is that you're going to get more protection the more corrosion inhibitor that you use. So depending on how that structure is going to be used in service and for how long that structure is anticipated to be needed, that will determine how much corrosion inhibitor is used. So if we have a little 2-lane highway going across the countryside and we've got a small bridge that's in disrepair and needs to be replaced, but we know long-range plans for that highway is to realign it, convert it to a 4-lane highway within the next 20 years or so. Well, we know that this little 2-lane bridge that we're putting in today doesn't have a very long service life. Maybe we're going to need it in use for 20 years. So we're not going to use very much corrosion inhibitor in that bridge compared to an interstate bridge where maybe we anticipate that bridge will be in use for 75 years. Okay, so depending on how long the structure is going to be in use and the exposure conditions for that structure, that will dictate how much corrosion inhibitor should be used. Because the corrosion inhibitor is sacrificial, the effectiveness of the corrosion inhibitor does decrease over time. Gradually, it will be used up. All right, so that is it for Chapter 1. Lauren, do we have any questions that have come up for Chapter 1?
We did have a couple of questions.
Okay.
The first one was about half an hour in. We had TM103 has the water weight at 8.34, yet the slide is showing 8.33 for a pound of water. Which would be best for calculating on the exam, or for a gallon of water?
Yeah. Either of those are going to get you the correct answer on the exam. Generally, as long as we have 3 significant digits in a value, then you're not going to run into any issues with round-off error or anything like that. The reason for the difference in that third number is one book you may look at may give the weight of a gallon of water as 8.34, another may give it as 8.33. It's that close. So that shouldn't affect the answer that you get when doing the calculation, no matter which of those 2 numbers that you use.
Okay, and then the next one we have on there is it possible that different providers of fly ash, like Gaston or Prairie State, do not chemically react the same with certain admixtures, ultimately affecting break strengths?
Yes, that's possible. Since the pozzolan, since the fly ash is a waste product, there are a lot of factors that come into play there. What type of coal was used? What the geology of the coal that was burned to get the fly ash? That will affect the performance of the fly ash. The loss on ignition, the carbon content will affect the performance. So yeah, that's definitely possible that fly ashes from different sources could behave differently, and even the fly ash from the same source could behave differently over a period of time.
All right, those are the only questions that came in.
Okay, well, we'll take a little break here between Chapter 1 and Chapter 2. I've got 2:37 Central Time, so let's take an 18-minute break, and we'll start back at 10 before. I'm sorry. Yeah, let's do that. Let's just take an 18-minute break and start back at 2:55.
All right.
All right, well, we'll go ahead and get started back with chapter 2. But before we jump into the chapter, did any additional questions come in during the break, Lauren?
No, no more questions came in.
Okay, thank you. All right, so for chapter 2, we're going to be talking about the essentials of quality concrete. And so we're going to revisit the materials that were discussed in chapter 1 and discuss some additional things to keep in mind with regard to those materials. But then we're going to look at the production process as well. We're going to look at proportioning, mixing, transporting, placing, consolidation, finishing, and curing. So we're not going to look at these in detail because there's a lot of information that would need to be covered if we did. But we're going to look at just some key things to keep in mind, some key essentials to keep in mind when looking at your production process. And then we're going to wrap up the chapter by with a little discussion on economizing both materials and the process. All right, so first let's talk about cement. Generally, we're going to use our mill certificates to give us an indication of whether or not the cement is meeting the desired parameters. Generally, the mill certificates indicate a chemical analysis that includes compound quantities for the different oxides that are present, and it also gives the results of physical tests. ASTM C150 is the primary ASTM that is used to govern the requirements for cement. And so generally it's going to be ASTM C150 requirements that we would be referencing back to. The mill certificate we would expect to indicate, to state explicitly that the material represented meets ASTM C150 requirements. So let's look a little bit at the chemical analysis. So there on your screen shows some of the oxides that are generally going to be shown on the mill report as far as what proportion of the overall sample was represented by each of these oxides. The sodium oxide and the potassium oxide are the two oxides that contribute generally to reactivity, if there's going to be any reactivity between the aggregates and the cement. The sodium and potassium oxides are not necessarily required to be indicated on the mill test report, but the testing is done by the cement supplier. So usually if I'm reviewing a mill test report and it doesn't give an indication of the sodium and potassium oxides or the equivalent oxides, that's a pretty good indication to me that it's probably pretty high content. So generally what I recommend to the plant that I'm reviewing their mill report is that they request that the cement supplier provide them with mill reports that indicate the alkali content because the cement supplier has the data, and so it's just a matter of putting the data on the mill report. And usually the cement supplier will be accommodating since they do already have the data. So it's the potassium and the sodium oxides that we're primarily concerned with. There are other limitations on the other oxides as well. But due to the potential for reactivity with aggregates, it's the sodium and potassium that generally we're going to pay the most attention to. Since there are different molecular weights between the potassium oxide and the sodium oxide, generally the potassium oxide is going to be normalized to a sodium oxide weight so that the total equivalent oxides can be stated as a function of sodium oxide equivalent. To be classified as a low alkali cement, that sodium oxide equivalent has to be less than or equal to 0.6%. Right, next let's talk about the Vogue compounds. These came up in chapter 1. The primary Vogue compounds are listed there on this slide. along with what they primarily contribute to the performance of the concrete. So C3S is the primary contributor to the early strength of the concrete. It reacts more quickly than some of the other components. C3A also contributes to the early strength gain, and similarly to C3S, produces more heat of hydration. So the reaction between the C3A and the C3S and the water generally produces more heat than the reaction with the other both compounds. C2S adds to the concrete strength as well, but it hydrates more slowly than C3S, so it doesn't contribute as much to the early strength gain as the C3S. C3A increases the early strength of the concrete, as would be expected, since it produces more heat of hydration. However, the C3A can adversely affect the late strength gain. So C3A may contribute to your initial strength, but it may negatively affect your long-term strength. C3A also has the problem that it contributes to sulfate attack. So a C3A content over 5% has an increased potential for sulfate attack within the concrete. And then C4AF doesn't really do a whole lot with regard to the strength. What it does do is it uses up any excess alumina. The A in C3A is alumina. So if we have a high C3A content, but we also have a high C4AF content, then the C4AF will help to offset the C3A as far as mitigating that potential for sulfate attack. So let's look at some potential compound compositions within a given cement sample. Now keep in mind that these are potential compound compositions. These are not required percentages. Just if you randomly sampled a particular type of cement, then this would be like an average compound composition that you might find. So let's talk through these a little bit. Looking at type 1, we can see that that this is kind of a general use concrete. And so the bulk of our material is going to be C3S. So over 50% is C3S. And then the next highest is the C2S. And then we've got C3A and the C4AF. Notice that the blame fineness is on average somewhere in the neighborhood of 370. Again, these are just some potential compound compositions. This isn't a requirement. But generally 370 is a good number that your blame fineness is going to be around. So type 1 is just a good general use cement. Now type 2 is a general use cement as well, but it has some sulfate resistance. And so notice that the key difference between the type 1 and the type 2 is that the type 2 has less C3A. Okay, so C3A is the contributor to sulfate attack. And so since type 2 has some sulfate resistance, it's going to have a lower C3A content. But other than that, and a redistribution of that percentage of C3A to the other components, it's very similar to type 1, and we have generally the same type of blame fineness. So we can have a cement that is a type 1, type 2, that it meets both qualification requirements. Right, look at type 3. Notice that the compound composition of type 3 is very similar to the composition of type 1. It's basically the same. A little bit of variation in the C3S, but other than that, it's basically the same. The big difference between type 1 and type 3 is that blame fineness. So essentially a type 3 cement is a type 1 cement that is ground more finely. We already learned from chapter 1 that the finer a material is, the more surface area it has. So when it comes to chemical reactions, generally the more surface area one of your reactants has, the more quickly that reaction is going to take place. And so that's exactly what we see here with type 3 cement. It's ground more finely than the type 1. It has more surface area available for reaction with the water, so it reacts more quickly. And so that's why we get higher early strength with the type 3 cement. It's not because of the chemical composition. It's a function of the physical characteristic of the fineness. It's going to react more quickly because it's been ground more finely. Then type 4 cement. This is a special use cement. Really don't see type 4 used very much. It's primarily intended to be used in large mass casts of concrete, such as for down projects where you have hundreds and hundreds of yards of concrete that are being placed in short order. And so for that reason, we want to have a fairly low heat of hydration. We don't want a high temperature differential throughout a large mass of concrete, because that can cause internal stresses and strains and lead to cracking. Generally, cracking is not something we want in a project like a dam. So notice that for the type 4, we have a low C3S. C3S contributes to early strength gain. C3A contributes to early strength gain. So we've got low amounts of both of those. So that's slowing the reaction process. Also, we have a fairly low blane fineness, 280 meters squared per kilogram. So again, that also helps to slow down the reaction. And so that's the purpose of type 4, is that it's going to cure more slowly. And we can see from the chemical composition as well as the blane fineness that it's been designed to do just that. Looking at the type 5 cement there, type 5 cement is has a higher sulfate resistance. So one of the key differences in the type 5 is that low C3A. So keeping the C3A low, because that contributes to sulfate attack. So that's the key thing there, is the low C3A. Look at the white cement. So a few things to notice in the white cement. One is that it has a relatively low C3S content. So that means that C3S is one of our primary contributors to early strength gain. So to kind of offset the low C3S, we have a high blane fineness. So the low C3S would indicate a lower early strength gain, but the higher blane fineness would indicate a higher early strength gain. So those two are kind of canceling each other out, so that we're kind of middle of the road when it comes to early strength gain. Notice that for white cement, that C3A is pretty high percentage, 14%. So what that means is that white cement may have a higher potential for sulfate attack than most gray types of cement. So this is one of the reasons why you're not going to see white cement used in any environment where exposure to sulfates or other chemicals is going to be likely. You're not going to see any white wastewater treatment plants because of the high C3A content and the higher potential for sulfate attack. All right, so again, those are just some potential compound compositions. Those aren't specified requirements or limitations or anything like that. On the previous couple of pages, that table that we were just looking at is on page 2.6, but on page 2.4 and 2.5, it shows the procedure for calculating the compound compositions for a cement sample. And so it shows you the 7-step process there on page 2.4, and then there's some nomographs that you would need to use in order to actually calculate these oxide percentages. So the good news is that this is a fairly easy process to go through. Even though it looks kind of complicated, these nomographs make it look a lot harder than it is. It's actually a pretty easy process. So that's the good news. The other good news is that you don't have to memorize any of this. You don't have to know how to do this process. So on page 2.4 of that 7-step process. You don't need to memorize that or anything. We just draw it to your attention so that you know how these oxide compositions are calculated in case you would ever be interested in looking at that more closely. So you don't have to memorize that, but it is a fairly easy process, easier than what the nomographs would indicate that it is. All right, as far as physical characteristics of our cement, there are several test values that are generally given on our mill test report. We've already talked a little bit about the fineness. The fineness can be reported according to two different methods, the Blaine or the Wagner. The Blaine is the more common. Some mill reports will provide both the Blaine and the Wagner results, but the Blaine is more common. So the higher the fineness number, the more surface area is present, and so the finer the material. All right, setting time. This is the time that it takes a water cement mortar to reach initial set. Just as a reminder from level 1 and level 2, initial set is when the concrete achieves 500 psi. So the setting time shown on the cement mill report is the time for a water cement mortar, so it doesn't have any aggregate. The setting time is controlled by the cement manufacturer by adding gypsum. Remember when we looked at the manufacturing process, there close to the end during final grinding is when the gypsum was added to the concrete. So based on the performance of the cement, the amount of gypsum that is going to be used will vary. The cement manufacturer will determine that value based on the setting time tests that they are conducting. All right, the setting time shown on the mill report is intended to provide relative information. Relative meaning that you could take one cement mill report and compare it to another mill report, and based on the set time that's reported, you can make certain assumptions as to how that cement would perform in your mix design. It does not give you the set time for your mix design. Water cement ratio will affect set time. The other proportions of other materials in the mix design will affect set time. So the set time reported on the cement mill report is not intended to give you this set time for your concrete mix design. Instead, it's relative information that will help you compare multiple cement samples. All right, there's a phenomenon that can occur in concrete mixing that's called false set. False set is when the gypsum that's been added to the cement reforms into a solid during the mixing process. And this looks like a stiffening or a hardening of the concrete, but it is not. It's just a material transformation of the gypsum going from a liquid state to a solid state. And so that's why we call it a false set. It's not an actual set resulting from the reaction between the cement and the water. The good thing about a false set is that if you keep adding energy, you keep mixing the concrete, that would usually reverse the false set and your slump will come back and you can use that concrete in your project. You don't have to throw that concrete away. False set is probably more common than people realize because it so often occurs while the concrete is in the mixer during the mixing process. And so for that reason, oftentimes it's not even noticed. One of the key indicators that a false set has occurred is if you get a spike in the amp meter on the mixer motor. That may be an indication that there was a false set for a few seconds, but because the mixer motor was running and energy was being added to the concrete, that false set was reversed and the slump came back. All right, so that's false set. There's another event that we need to be aware of, and that is a flash set. Okay, a flash set is a rapid hardening of the concrete that results from the reaction between the cement and the water. So flash set is a real set, and if that occurs while the concrete is in the mixer, then we need to act quickly to start getting the concrete out of the mixer. No matter where the concrete is at, if we get a flash set, we need to act quickly to get the concrete out of that container. Otherwise, we're going to have to spend a lot of time with jackhammers getting the concrete out. So flash set is a real set of the concrete. It's not reversible, and we cannot use that concrete. That concrete has to be discarded. A false set is not a true set. It results from the gypsum transforming its physical state. And if a false set occurs, it can be reversed and the concrete can be used. Right, air content is another item that's indicated on the mill report that can be determined by ASTM C185. Autoclave expansion is covered by ASTM C151. Autoclave expansion is an indication of unsound cement. We don't really have a problem with unsound cement in the concrete industry today. In years past, it has been an issue, but with tighter controls on the materials that go into the cement and the cement manufacturing process, the occurrence of unsound cement has become almost non-existent. What happens with unsound cement is that if the cement is used to make concrete while the cement is still hot from the manufacturing process, then it can over time lose durability. And so this unsound cement phenomenon was observed when cement plants had concrete block plants that were next door to them. So that was very common in decades gone by, that the cement producer would also be a concrete producer. And so one of the items that they would use their cement in would be concrete blocks. And so they would have a block plant next door to the cement mill, and they would ship hot cement over to the block plant, which would then get used. And there were some instances where the blocks would come out after initial curing and look fine, have sufficient strength, but then over a period of days, weeks, months, the concrete would kind of self-destruct. It would start falling apart. And so they referred to this phenomenon as unsound cement, and they developed this test, ASTM C151, as an indicator of whether or not the cement would perform this way. But anymore, we don't see a lot of hot cement being shipped out to buyers. So that's one of the reasons why we don't see this occurring very much. And also just the tighter controls on the raw materials and the manufacturing process that goes into cement production. Right, compressive strength is also indicated on the mill report. The compressive strength that's indicated is the result of 2-inch mortar cubes. So again, no aggregate is involved. It's just a cement water slurry, cement water mortar, and 2-inch cubes are tested. Whether or not the cement is a type 1 or a type 3, there are different requirements for what kind of minimum strengths should be attained and over what period of time that those strengths should be attained. Just like the setting time information is provided so that you can make a relative assessment between different cement samples, is the same thing with the compressive strength. This compressive strength is not indicative of what your compressive strength is going to be with your mix design. It's purely intended to be relative information so that you can make an assessment of how one particular sample is going to perform relative to another sample. So the compressive strength indicated on the mill report should not be extrapolated out to estimate a compressive strength for your mix design. Loss on ignition, we talked about this test with regard to fly ash. When used with fly ash, it's an indicator of the carbon content, but it can also be used with cement as an indicator of the moisture content. The higher the moisture content of the cement, the more of a concern that is. The cement reacts with moisture, and so the more moisture that's available in the same environment as the cement, the greater the likelihood that the cement will react prior to when we want it to react, which is after it's been combined with water and other materials in our mixer. So a good rule of thumb is that if cement has lumps, hardened lumps in it, that's an indication that it has been exposed to moisture. If you can break up those lumps with finger pressure, then the amount of moisture exposure is not too high. It's acceptable. If you cannot break up the lumps with finger pressure, then the moisture exposure has been too high, and that cement sample, that cement stockpile should be discarded, and new cement should be used. Another physical property is insoluble residue. This is the amount of material other than the components that we want to be in the cement. So this is essentially other stuff. ASTM C150 limits insoluble residue to less than 0.75%. For domestically produced cement, generally we're going to be well under this limitation. So due to the tight quality control on cement production, usually the insoluble residue is going to be well below 0.75%. Right, uniformity of cement. This is just an indication of the average daily test from a silo. So generally what the plant is going to receive, the mill report they're going to receive is going to be a combined average for all of these different test values. The cement mill will do testing on a regular basis while cement is being produced, but that cement is dumped into a silo and it's blended with other days of production, such that the mill report will have average test data for a given month. And that's usually what the plant will receive, is a monthly mill report indicating the average test data for that cement over that month. All right, let's talk a little bit about aggregates. So we want to make sure that we're controlling certain aspects of our aggregates to ensure that we get the proper performance from those aggregates and we get consistent production of quality concrete. So the uniformity of our aggregate is with regard to the material that is being used, the geology within the aggregate. We want aggregates to generally come from the same geological formation so that we're not getting variation in the materials that make up the aggregate. Generally, we want to have control on the moisture in our aggregate. We can do that in a couple of different ways. One is we can control the environment of the aggregate. So we can keep aggregates covered, we can keep them sprinkled to maintain a consistent level of moisture. Another thing that we can do is we can do regular testing of the moisture content and then make adjustments based on the actual moisture content of the aggregates. Essentially what most precast plants do is a combination of those two things. Generally, we want to control the moisture content and keep it as consistent as we can, but at the same time, we're going to do regular moisture testing so that we know how much variation is occurring and we can account for that variation in the batching of the aggregates. We also want to have gradation control. We want our aggregates to be consistent in gradation from one shipment to the next. We should be doing regular gradation testing at the plant. PCI requires that for most plants that they do a gradation test for a given aggregate at least once per week. If the aggregate is in heavy use, you may have to do more frequent testing. But for bridge and commercial products, each aggregate that is in use should have a gradation test conducted at least once per week. If it's an architectural aggregate, like a face mix aggregate, that the volume of the aggregate that is used is pretty limited, then the requirement is that a gradation test be done once every 2 weeks. All right, so that's gradation testing requirements. We want to make sure that for any variation that we encounter, that we are making appropriate adjustments to our mix design. The most common adjustment to our mix proportions is going to be due to moisture. If we have a shift in the gradation of the aggregate or a shift in the fineness modulus of the aggregate, then we may need to adjust our mix proportions. That does happen, but that is much less frequent than the adjustments we would make for the moisture variation within our aggregates. All right, acceptance testing of our aggregates. A number of ASTM tests that can be used for acceptance testing are shown there on your screen. There are many, many more that can be used. It seems like every few years there's another ASTM test that comes along that can be used to evaluate the acceptable performance of an aggregate within concrete. So these listed here are the ones that have been around the longest, but there are others that can also be used. Some of these are long-term tests that may take a year to complete. Others are short-term tests that may be able to be done over a period of a few weeks. So oftentimes what a plant will do is they will do the short-term tests so that they get a pretty quick result. If that result indicates that there are no issues with reactivity or what other factor was being evaluated, then we say that the aggregate is acceptable for use and we move on. If the short-term test, which tends to be less accurate than the long-term test, indicates that there is a potential issue with reactivity or some other parameter, then we may go ahead and do a long-term test as well, just so that we have better information with regard to just what level of reactivity that aggregate is actually at. All right, so a number of tests that can be used for evaluating our aggregates and their suitability for use in concrete. The petrographic analysis of aggregates, ASTM C295, is a common requirement that PCI has in place for architectural aggregates. Pretty much any architectural aggregate should have a petrographic analysis completed. If that analysis indicates that there are potential issues, then additional testing may be required. Petrographic analyses can be expensive, so if the aggregate supplier is not providing test data and it's up to the plant to get the aggregate tested, then what they may do is, instead of having the petrographic analysis completed, is they may do one of these potential reactivity tests just to kind of cut the corner off the testing process and determine whether or not there's any potential reactivity. Now keep in mind that the reactivity of the aggregate is of primary concern to us, but there's also other things that are of concern that the petrographic analysis could give us an indication of. One of those may be the amount of iron in the sample. Iron in an aggregate sample tends to cause rust stains over time, and so that usually doesn't adversely affect the structural performance of the concrete, but it certainly affects the aesthetic performance of the concrete. And so that's something that would be good to know. So petrographic analysis is not just to give an early indicator of reactivity, it also gives an indicator of other potential issues. Next, revisiting admixtures. Just a few things to keep in mind when using admixtures in our concrete. One is compatibility. Admixtures don't always interact with each other well. If all of your admixtures come from the same admixture supplier, that supplier is well aware of how their different admixtures interact with each other, and they can give you guidance on which admixtures should be used with each other and which admixtures should not be used with each other. Where we run into issues is if for some reason you're using admixtures from different admixture suppliers. Generally, there's not going to be much information available with regard to how those admixtures from different suppliers interact with each other. And so we have an increased risk of getting a reaction between two admixtures that is not a desirable reaction if we're using admixtures from different admixture suppliers. So this is one of the reasons why most precast plants will use all admixtures from the same supplier. There's a number of good suppliers out there. Sika, Master Builders BASF, Euclid, I can go on and on. There's a number of them out there. As long as a plant is using admixtures from the same admixture supplier, usually compatibility is not going to be an issue because their admixture rep will give them guidance. But if for some reason the plant is using admixtures from different admixture suppliers, that increases the potential for interaction between those admixtures. All right, the batching sequence can affect the performance of the admixture. Generally, again, your admixture supplier will be the best source of information with regard to when each particular type of admixture should be introduced into the mixing process. If we have two admixtures that are known to interact with each other, but if we introduce them into the mix at separate times, then we may be able to avoid that interaction and still use those admixtures together. So make sure that you're in close contact with your admixture representative and getting advice from them with regard to the sequencing of your batching process for the admixtures. Chloride content, we've already touched on this a little bit, but the chloride content for concrete is limited significantly if it is pre-stressed concrete. This will come up again in a later chapter. But because chlorides can be introduced into the concrete through admixtures, it's important that the plant is aware of the chloride content within the different admixtures that they're using, and that they are using admixtures with low or no chloride contents so that they can avoid any potential issues with corrosion. For pre-stressed concrete, this is especially important because high strength steel that is under a sustained stress is more susceptible to corrosion. And with pre-stressed concrete, that's exactly what we've got. We've got high strength tendons that are under a sustained tensile load. And so due to that increased potential for corrosion, for pre-stressed concrete, the chloride content is limited to 0.06% max by weight of cement. For non-pre-stressed concrete, the chloride content is still limited, but it is a much more liberal limitation than for pre-stressed concrete. All right, next let's talk about water a little bit. Generally, if the water is potable, which means that it's drinkable, then it's generally acceptable for use in concrete. That's especially true if it is from a municipal source. So if the precast plant gets their water from a municipal source, then unless there are indications otherwise, it is assumed that that water is acceptable for use in concrete. If the water is non-potable or it's a questionable source, it's either not drinkable or we don't know if it's drinkable, then testing is required to determine whether or not it is acceptable for use in concrete. So the first round of tests that we should do are shown in table 2.2. So these are a couple of different tests. We should make samples using a known good water source and samples using the questionable water source. And we should test our compressive strength at 7 days and the set time for the two concrete samples. so long as the compressive strength of the questionable sample is within 90% of the control sample, and the set time of the questionable sample is from 1 hour earlier to 1.5 hours later than the control sample, then that is an indication that the questionable sample of water may be acceptable for use in concrete. Right? Passing these two tests does not make it acceptable. It just leads us to the next set of tests that are shown in PCI MNL 116. All right, so these two tests on compressive strength and set time are just to kind of open the door to the water sample. If it can't pass either of these two tests, then it shouldn't be used. If it can pass these two tests, then there are some chemical analyses that we need to do just to make sure that there aren't any chlorides in it, that there aren't any other deleterious substances that would potentially adversely affect its performance in concrete. But generally, if it doesn't adversely affect strength or set time, that's a good indication that the water is probably going to be okay for use. All right, sometimes we use wash water in the batching process. This is especially true for ready-mix concrete. And so if wash water is going to be used as a component of the concrete, then we need to do some testing on the wash water to make sure that it meets certain requirements before we can clear the use of the wash water. So shown in table 2.3 are the primary requirements with regard to chlorides, sulfate, alkalis, and total solids. So as long as our wash water meets these limitation requirements according to these test methods, then we can use a portion of the wash water as mixing water in our concrete. So that's the batching process. Now let's talk a little bit about mixing. So batching tolerances are given in table 2.4 on page 215. And so for our cement, the tolerance on batching of cement is plus or minus 1%. For water in your book, it says plus or minus 1.5%. That's a typo. It should be 1.0%. Or for smaller batches, we may switch over and use the plus or minus 1 gallon. But generally in precast plants, we're batching sufficient volume that the tolerance on water is plus or minus 1%. For fine aggregates, it's plus or minus 2%. Coarse aggregates, it's plus or minus 2%. But cumulative aggregates, it's plus or minus 1%. And so sometimes people look at that and they think, oh, that's backwards. That it's 1% on each aggregate, but you get 2% on the total. No, what's shown there in the table is correct. You have a more liberal tolerance on individual aggregates than you do on the cumulative aggregates. So for individual aggregates, you have that 2% allowable variation. But for all of your aggregates combined, that total weight should be within plus or minus 1% of the target weight. For admixtures, the tolerance is plus or minus 3%, or we have some other tolerances that may come into play based on the size of the batch. Generally, this plus or minus 3% will control in most precast plants due to the batch size of concrete that is being mixed. All right, uniformity is another requirement, table 2.5. This comes from ASTM C94, which is the ASTM standard with regard to ready-mix concrete. So this requirement, these requirements for uniformity are generally applied to truck mixed concrete. All right, centrally mixed concrete, generally we don't have these uniformity requirements. You could still use this uniformity parameter to do a uniformity test on centrally mixed concrete, but generally centrally mixed concrete is going to meet these requirements. It's truck mixed concrete that this is primarily intended. So this is a little bit different testing than what we're accustomed to. This is test results. We're averaging and comparing test results from within the same batch or the same truck of concrete. So the way this uniformity testing would work is we would take a concrete sample off the front end of the truck, do our testing. We would take a sample off the middle of the truck, do our testing, and then we would take a sample off of the back end of the truck and do our testing. And then we're going to compare our different test results to each other. And if our concrete is being produced uniformly, acceptably uniformly, then the variation in those test results is going to meet these requirements. So the weight per cubic foot of our fresh concrete is going to be within 1%, 1 pound per cubic foot between our three tests. The air content is going to be within 1%. The slump is going to be within 1 inch if it's a low slump mix, or 1.5 inches if it's a medium slump mix. And it's not shown here on the table, but usually we use 2 inches if it's a higher slump mix. Our coarse aggregate content should be within 6% over our three samples. The unit weight of the mortar should be within 1.6%, and the average compressive strength at 7 days should be within 7.5%. All right, so again, this is three samples that are taken from the same truck, and basically this is an indicator of how uniformly that truck is capable of producing a batch of concrete. So this isn't testing that has to be done daily, but it should be done on a regular basis in accordance with ASTM C94 to evaluate how efficiently and effectively a truck mixes concrete. So if when doing this uniformity test, it's found that some of these requirements are not met, that's usually an indicator that the truck needs to be removed from service and it needs to be renovated, which means that the barrel may need to be cleaned out. Maybe that the mixing fins within the barrel have worn so that they're no longer as effective as new fins would be, so the fins may need to be replaced within the barrel. But generally, if the truck cannot meet these requirements, then that truck should not be used for production. Mixing time is generally going to vary with the volume of the concrete that's being produced. Over on page 217, there are some rules of thumb for how long a batch of concrete should be mixed. These are rules of thumb. Keep in mind that the mixing time is going to vary, not only with the volume of the concrete, but also with the type of mixer that's being used. If you have an old pan mixer that needs to be refurbished, then your mixing time is probably going to be significantly longer than if you have a twin shaft, new mixer, high shear mixer that has a lot of mixing power. Generally, you're going to be able to batch, or you're going to be able to mix rather a batch of concrete much more quickly with a dual shaft new mixer than you would with an old pan mixer. So keep that in mind. These rules of thumb time vary not only with the volume that's being mixed, but also with the type of mixer that's being used. There's some requirements here for truck mixing. Notice that generally for truck mixed concrete, it should be mixed at 70 to 100 drum revolutions at the manufacturer's recommended mixing speed in order to say that that concrete has been fully mixed. After the concrete has been fully mixed, if we make any adjustments to the concrete mix, such as adding some admixture, adding some water if we've held out a little bit of water during the initial batching, so that we have the opportunity to add a little bit of water back. Then anytime we make an adjustment to the mix after it's been initially mixed, then we need to remix the concrete a minimum of 30 drum revolutions at the manufacturer's recommended mixing speed. So this is one of the reasons why some plants use mixer trucks to deliver concrete to their beds. It's so that they can make small adjustments to the concrete at the bed. There's nothing wrong with doing that. Most of the time, these plants are not using the truck to actually mix the concrete. They're centrally mixing the concrete and then using the truck just to transport the concrete to the bed. But whether the truck mixed the concrete initially or it was centrally mixed initially, if any adjustments are made to the mix at the bed, any adjustments to the amount of water, any adjustments to the admixtures, then that concrete needs to be remixed a minimum of 30 drum revolutions. So if I'm doing an audit at a plant that transports their concrete in mixer trucks so that they have this capability of adjusting the concrete at the bed, if I see them making any adjustments at the bed, then I'm going to be looking to see if they remix the concrete a minimum of 30 drum revolutions. So if I'm at your plant doing an audit, you transport concrete in this way, you make changes at the bed, then if I'm watching this while this concrete is being remixed, if you looked over at me standing to the side watching the process, I might look a little funny because my head is probably bobbing up and down. And it's bobbing up and down because I'm watching that drum and I'm counting the drum revolutions. And so long as they remix the concrete a minimum of 30, that's acceptable and there are no issues, assuming that the truck is in good working order and that it's capable of actually remixing the concrete. If they do not mix the concrete a minimum of 30 drum revolutions after making an adjustment to the mix, then that would be a nonconformance for the audit. All right, next is transporting concrete. If we're transporting the concrete by a device that agitates the concrete, then segregation during transport is usually not going to be an issue. But oftentimes a plant will transport concrete by means that do not provide agitation. Some examples of this would be a Tucker-built truck, a bucket on a forklift, a bucket on the back of a truck. So any transportation of concrete that doesn't involve agitation of the concrete, it's fine to do that. There's just some things we need to keep in mind. One of those is that we need to keep the drywalls between the batch plant, between the mixer and the production area. We need to keep those nice and smooth so that vibration during the transport doesn't cause segregation of the mix. This is especially important in this day and time when self-consolidating concrete and flowable concrete is more the norm than the exception. Those higher slump flow mixes are more susceptible to segregation due to vibration than lower slump mixes are. So if you're using a flowable mix or a self-consolidating mix, you're transporting that by a method that doesn't involve agitation. You want to make sure that you're regularly running a blade over your drywalls just to fill in any potholes, to knock off any high areas so that as that transport is being conducted, the concrete is not being vibrated and segregated as a result. All right, placing and consolidation. So we're just working our way through the manufacturing process. A couple of rules of thumb when it comes to placing concrete. Generally, we want to place the concrete as near as possible in the form to its final position. We don't just want to dump the concrete in a big pile right in the middle of the form and then have to use come-alongs or shovels or other means to then move the concrete to fill in the rest of the form. We want to try to place the concrete uniformly so that a minimal amount of effort is needed to move the concrete and distribute it throughout the form. We also want to minimize the fall of the concrete from the chute, from whether it's a bucket or a mixer truck. We want to get the chute as close as we can to the form surface and minimize that fall. The more fall the concrete goes through, the greater the energy that it gains as it falls, and the greater the likelihood that it will segregate when it hits the form. So we want to minimize the fall. Now, both of these rules of thumb primarily apply to normal slump mixes. If it was a self-consolidating mix, then generally, depending on the product that's being cast, we're going to pour the product from one location and allow the concrete to flow and fill the form, because that is the process of self-consolidation. It's the energy of the flowing concrete as it fills the form that's helping to consolidate the concrete. All right, so these rules of thumb here on the slide are for normal slump mixes. For flowable mixes or self-consolidating mixes, placing it as near as possible to its final position isn't really something that we would try to do. We would want that concrete to flow so that it gets consolidated. Whether it's a normal slump mix or a higher slump mix, we still generally want to minimize the fall from the chute, just so when the concrete splatters on the form, it doesn't segregate. All right, consolidation of concrete. If it is a high slump mix, then we need to be careful to avoid over vibration of the concrete. If it's a low slump mix, then we need to be careful to avoid under vibration. So generally, we're going to be pouring mixes today that would fall more in the higher slump range than the lower slump range. So over vibration would be our biggest concern. Another rule of thumb for an architectural face mix is that generally you want to place the full face of the panel from one batch of concrete. There may be some variations in the water cement ratio of one batch to the next that can cause slight variations in color. That if we put both of those batches in the face of a given panel, then we might be able to see that variation. But if we cast the full face of a panel from one batch of concrete, then generally we're going to avoid the potential for seeing that slight variation in color. Once the concrete is placed in the mold, we're usually going to wait to vibrate that concrete until after that full face has been placed. There are different methods of vibration that can be used, and we'll talk about those in just a minute in the next section. But generally, we want to place the full face of an architectural face mix before we start vibrating that concrete. Whatever method we're using to consolidate the concrete, generally we want to avoid touching the form with our vibrator, except unless it is an actual external form vibrator, then obviously the vibrator would be touching the form. But for any other form of vibration, we want to avoid touching the form surface, as it can cause localized amplification of the vibration that can cause segregation in that localized area. For internal vibrators, there's a couple of figures there in your book on page 220. So each internal vibrator has a radius of action. And so we want to insert the internal vibrator into the concrete, let it fall under its own weight to the desired elevation, and then withdraw the vibrator uniformly at a uniform speed, and then repeat the process. And we want to do that in drops such that the radius of action overlap with each other. So for each drop of the internal vibrator, the radius of action should overlap. We want to avoid turning the internal vibrator on and off while it is in the concrete. That can cause void space within the concrete, so the internal vibrator should always be running when it's inserted into the concrete and remain running until it is removed from the concrete. Also, we want to make sure that if we are placing the precast unit in multiple lifts of concrete, that the internal vibrator penetrates the current lift that's being cast and goes into the previous lift so that we get good consolidation across that boundary layer between the two lifts of concrete. We don't end up with a cold joint at that location. All right. Continuing placing and consolidation, form vibrators. Form vibrators come in a variety of vibration speeds or frequencies, usually anywhere from 3,000 to 12,000 vibrations per minute. Generally for a lower slump concrete, we want to have a lower frequency, higher amplitude vibration. For a higher slump mix, we want to have a higher frequency, lower amplitude vibration. So there's a couple of technical terms here that we're using, frequency and amplitude. And so just a quick refresher on what those two terms mean. Frequency is the speed at which the vibrator goes through a cycle. So if it's a 12,000 vibrations per minute, then that means you can calculate out, divide that by 60, and you get like 200 vibrations per second that vibrator is going through. So that's the frequency. 200 vibrations per second, 1,200 vibrations per minute. Okay, the amplitude is the physical movement of the vibration. So a good example of a low frequency, high amplitude vibration would be what's called a shock table. Many of you that are attending this class have probably never seen a shock table. I've only seen it a handful of times, and that was years and years ago. But some plants were set up, architectural plants were set up to where their forms, their flat forms were movable. And what they would do is they would cast the concrete in the form, and then they would use their overhead crane. They would pick the form up and move it over to a device that was called a shock table, which was basically just a big hydraulic lift. And once the form was set on the shock table, they would activate the shock table and it would physically lift the form and then drop it. And so this is a good example of low frequency, high amplitude vibration. It was low frequency. You could actually see the shock table going through a cycle of lifting the form and then dropping it, lifting a form and dropping it. It would go through a cycle of maybe 1 per second. It was high amplitude because you could actually see the displacement of the form. It would be lifted several inches and then dropped several inches. So that's low frequency, high amplitude vibration. Okay, the other end of the spectrum, high frequency, low amplitude vibration is what you would commonly see today on forms that have external form vibrators attached. They vibrate at a very high frequency. They sound like a bee buzzing, just very, very high pitched. So that tells you it's a high frequency. But the amplitude is very low. The amplitude is so low that you can't actually even see the form moving. You definitely hear the vibrator running, but until you go up to the form and actually put your hand on the form, you don't even know that it's moving. You have to kind of feel the movement because it's such a low amplitude movement. So that's an example of a high frequency, low amplitude vibration, which would be more common today because we're more commonly using higher slump mixes today. Right, vibrating screeds, these are great devices because you're accomplishing two things at the same time. You're striking off the unformed surface of the concrete at the required elevation, and you're smoothing that surface, but you're also consolidating that surface. So with one operation, you're striking the concrete, you're smoothing it, and you're consolidating that surface. If it's a very thin element, such as a 2-inch flange on a double T, then you need to be careful to not over vibrate that concrete. Such a thin section of concrete, you need to move the vibrating screed along pretty quickly, or you'll cause segregation in that flange. Vibrating screeds are great for flat work, such as the flanges of double Ts, or for wall panels. They can be effective with their vibration up to 8 inches or so, just depending on the energy that's being dissipated by the vibrating screed. So very, very good devices, accomplish a lot in a short period of time. Another method of consolidation is a grid or plate vibrator. You most commonly see these used in architectural production to consolidate the face mix of an architectural panel. The way these work, or what these look like, is you either have a steel plate or a grid that maybe it's between 1 and 2 square feet of coverage. It has a vibrator attached to it and a handle so that a worker actually gets into the form after the face mix has been cast and smooth. They walk on that concrete and they place this grid or plate vibrator down and allow it to vibrate every square foot of that face mix for a set number of seconds. So the advantage to using a grid or a plate vibrator is you get very uniform vibration throughout the full surface of the panel. The downside to using a grid or a plate vibrator is that it is time consuming. It takes a while to set that plate or grid vibrator down, let it vibrate for a few seconds, pick it up, set it down again, pick it up, set it down again, and keep moving it until you've got that whole panel surface covered. So it's very effective. You get very nice looking architectural finishes, very uniform distribution of your aggregate within the face mix, but it is time consuming. Right, next is finishing. So usually the first step in our finishing process is going to be to screed the concrete off at the desired elevation. Oftentimes our screeding also helps to smooth that surface, depending on what type of screed that we're using. We can further smooth the surface using a float, oftentimes referred to as a bull float. If it's on a handle and covers a larger area, we would call that a bull float. If it's just a float that's held in the hand, then we would refer to that as just a float. So a float is a hand float, but then we can also have a bull float that covers a larger area that's attached to a handle, and then we would have our final finishing. Sometimes surfaces receive a composite concrete finish. This is an intentionally roughened surface so that the surface will bond well to a subsequent cast of concrete. Most commonly, we see a composite concrete surface on products like box beams, bridge girders, sometimes on double T's. It just depends on the geographic area of production. In some parts of the country, the whole double T will have a composite surface because in order to meet seismic requirements, they have to do a cast-in-place slab on top of the double T. In other parts of the country where seismic concerns aren't as great, they can cast the full thickness of the double T flange and not have to do any composite concrete. So you can see it done both ways. So double T's is one product, bridge girders and box beams are probably the most common products that we see cast with a composite concrete surface. We want to make sure that that surface, when it's roughened, that it is clean and free of latents. Latents is just loose concrete material. We don't want to wait so long to do the roughening of that surface that the roughening actually just pulls coarse aggregate particles out of the surface of the concrete and then leaves them loose on the surface. That would be latents. We want to do the raking fairly soon after the floating process, just so the concrete needs to be stiff enough that it will hold the rake, but not so stiff that we're actually pulling coarse aggregate particles out of the surface of the concrete and causing loose material, leaving loose material behind. Okay, let's talk a little bit more about the float finish process. Generally, floats are going to be either wood or magnesium. As I said, that can be either a hand or a bull float. Generally, we want to have a minimal amount or no bleed water on the surface when we do our floating. If there's an excessive amount of bleed water, then we either need to wait for that excessive water to evaporate, or we need to remove that water from the surface. One way that we can do that is by using our screed to pull the water off the surface. Or another good method is to use a garden hose. You can drag that garden hose across the surface and kind of collect the water and pull it off to the side, allow it to drain. But generally, we want to have little or no bleed water on the surface when we apply our float finish. The primary purpose of the float finish is to embed those larger aggregate particles so that they're not sticking out of the surface and interfering with the smoothness of the surface. This also helps to remove imperfection and helps to compact the surface of the concrete, the unformed surface. So that's float finishing. Next is broom finishing. Oftentimes a broom finish will be applied to a concrete surface that is going to have either vehicular traffic or foot traffic. The broom finish helps to ensure that there is adequate friction should the concrete surface be wet, so that a car can get traction and so that people don't slip when they're walking on that surface. So one of the most common products that we see with a broom finish would be a pre-topped double T for a parking garage. Usually the broom finish is applied fairly soon after the floating operation. Depending on the mix design, we want to make sure that we choose the correct broom as far as the stiffness of the bristle. We want the bristles to be stiff enough that they actually etch the surface of the concrete, but not so stiff that they're actually pulling particles out of the concrete and overly roughening the surface. All right, a trowel finish. This is a smooth, hard finish that is generally applied to products like the backside of wall panels. We can apply a trowel finish using either a hand trowel or a machine trowel. We can also have a bull trowel, a trowel on a long handle to cover a larger area. Generally, the more passes we make on the concrete surface with the trowel, the harder and smoother that surface is going to be. For finishers who really know what they're doing and when it's required, they can get such a hard, smooth finish on concrete that it's almost like a mirror. It's amazing what some of these guys can accomplish. Of course, it takes a lot of effort to do that, so generally a plant is not going to put in the time and effort for a really smooth trowel finish unless that's what the project requires and the project has been priced accordingly to account for the labor that's going to be required to install such a trowel finish. One thing to not do with a trowel is to use a trowel in place of a float. Floats have rounded edges. That's on purpose so that they don't seal up the surface of the concrete. A trowel does have sharp edges, and those sharp edges are intended to seal up pores and small openings in the concrete. So if you use a trowel when a float should be used, that means there's still a decent amount of moisture within the concrete that may be making its way to the surface. So if you use a trowel when the concrete is still fresh, then you may be trapping moisture under that surface, increasing the water cement ratio of that surface, which leads to a weak surface that over time is going to peel and flake away. So we do not want to use trowels when a float should be used. So just keep that in mind. Other finishes that can be applied to the formed surface of the concrete. Sometimes if we have an excess amount of bug holes, then we may need to sack rub the formed surface to fill in those bug holes, smooth those out. As far as architectural finishes are concerned, we have sandblasting, retarded or exposed aggregate, and acid etching. Those create a uniform finish on the surface of the concrete that is to the specified aesthetic requirements. So with sandblasting, we have more variety. We can do a very light sandblast that just does a light etch on the surface, or we can do a heavy sandblast that actually exposes the coarse aggregate and allows the coarse aggregate to project from the surface of the matrix. Usually with acid etching, it's just going to be a light etch just to take the shine off of the surface. And then of course with retarded or exposed aggregate surfaces, we can use a retarder to retard the set of the matrix on the surface, and then we can pressure wash that matrix away shortly after the product has been stripped from the form, so that we expose most of the aggregate on that surface. And depending on what type of aggregate we're using, we can have a very beautiful finish that could be multicolored, or there's a lot of different color aggregates that can be used. So retarded is one of the most common architectural finishes that's been around for so long, just because you can achieve a good uniform finish that architects like. Then on just regular commercial and bridge form finishes, generally form finish means that as it comes out of the form, that's what the customer gets. Generally for bridge and commercial products, that is satisfactory. One thing that we do need to do is remove fins from sharp edges. Either rub a grinder or a rubbing stone over corners and edges, just to remove fins and clean those up a little bit. But otherwise, a form finish is a form finish, and it's just as it comes out of the form. All right, curing, and then we'll talk a little bit about economy and wrap up chapter 2. So for curing, the requirements are going to vary depending on the mix design that is used and the product that is being cast. If we have a mix design that incorporates silica fume, then we may need to have water applied to the unformed surface just to make sure that that surface does not dry out and we don't get plastic shrinkage cracking. We can do that by covering the surface with burlap and then soaking the burlap. We can flood the surface, or we can keep a sprinkler on that surface so that we maintain 100% moisture on the surface. We can also retain the moisture that's inherent within the concrete. We can do that by spraying on the unformed surface a moisture retardant. More commonly, instead of spraying a moisture retardant, we're going to use a plastic sheet or a tarp to cover that surface and help to retain the moisture that is naturally evaporating from the concrete surface itself. We can also create a moist environment by using a kiln. Kilns were more common for some types of products that we don't see produced a whole lot anymore. There was a type of hollow core plank that was produced in movable forms called Flexicore. So some of you may be familiar with Flexicore. Don't see a whole lot of Flexicore anymore. But in the manufacturing process, the forms could be moved into a kiln, and so that way they could be heat and moisture cured. And so that's also an option. Still see that done in some plants that produce utility products like pipe, manholes, those sorts of things. Some plants still have an area that can be curtained off and heated and steamed to produce a kiln environment. Accelerated curing is common in precast plants. This is where we add heat to the initial curing process in addition to the heat that is generated by the concrete as it cures. There's a few different ways that we can add heat. We can use what's called live steam. Live steam is when we have steam lines running around the bed or under the bed. that have holes drilled in the lines so that the steam is actually released into the curing environment and provides not only heat but also moisture. We can have radiant steam, which is a closed system. We get the heat from the steam, but we don't get the moisture from the live steam. We can use radiant hot water, so we don't have to heat the water to the point that it's steam, but it is heated water or heated oil that's circulated around the bed just to heat the concrete. And then we can also have radiant electric elements attached to the form to provide the heat. There are some requirements that we have to meet if we're using accelerated curing. These are given in MNL 116. The requirements that are shown on this slide are from 116.99. Some of these have not changed, some of these have changed, but the numbers that we're showing here on the slide are the correct numbers. So whether you're looking at 116.99 or the newer 116.21, the numbers in the 99 code are maybe different from these numbers shown on the slide, but the numbers shown on the slide are the current requirements. So just in passing, in MNL 103, there are some things that we'll touch on that the manual has numbers that have been updated. The exam is based on the current requirements, not on the dated requirements in the manual. So as we come to those, I'll try to remember to point those out to you in the manual so that you can make a note in your manual of what the current requirement is. But the exam is based on current requirements. And so where current requirements deviate from what's shown in the manual, it is the current requirement that you should know. So the requirements for accelerated curing are we can only raise the temperature of the concrete a maximum of 10 degrees per hour up until the concrete reaches initial set, or until the concrete reaches 104 degrees Fahrenheit if it's pre-initial set. Okay, so we can heat the concrete, but only 10 degrees per hour up to a maximum of 104 degrees Fahrenheit unless the concrete has reached initial set. If it's reached initial set, then this requirement no longer applies and we can heat the concrete up more quickly. Initial set, just as a reminder, is 500 psi. It is determined by ASTM C403 by separating out the coarse aggregate from a sample of your mix design and then using a penetrometer over a period of time to determine when that sample, that mortar sample reaches a strength of 500 psi. Once we've reached initial set, we can heat the concrete up a maximum of 36 degrees per hour up to a maximum of 158 degrees. In your book, it says, this is on page 226, and the second paragraph from the bottom, that last, next to last sentence, it says that it must be kept less than 190 degrees. So that has been changed. The maximum concrete temperature that is allowed is 158 degrees. So if you want to mark that in your book, 158 degrees. As the book does note, there's little advantage in heating the concrete much above 150 degrees. So in recognition of that and research that has shown that we can actually adversely affect the long-term durability of the concrete by heating it much above 150 degrees, they went ahead and lowered the maximum allowable temperature to 158. So that's where that came from. If you look at this next slide, this shows the 3 stages of the initial curing of concrete. This is not in your book, but it is something that you've probably seen in level 1 and level 2. So stage 1 is that period from when the concrete is mixed until it reaches initial set. During stage 1, we have limited heat that we can apply to the form because we need to keep that temperature less than increasing 10 degrees Fahrenheit per hour up to a maximum of 104 degrees. Once we reach initial set, then we can jump up to the 36 degrees per hour up to a maximum of 158. We refer to this as stage 2. This is a period of 8 to 10 hours over which the concrete increases in strength at a pretty significant rate. 500 to 700 psi per hour is not uncommon, or even higher than 700 psi per hour. After stage 2, we go into stage 3, which is a period where the concrete is still gaining strength, but it's at a much slower rate, generally in the 50 to 100 psi per hour strength gain range. All right, so those are the 3 stages of initial curing. As far as economy is concerned, we've talked about a lot of different things in this chapter. We've talked about our materials. We talked about cement, admixtures, our aggregate. We've talked about the manufacturing process, from batching and mixing to placing, consolidating, finishing. So we've looked at pretty much the whole process. And so that's why they placed the discussion on economy at the end of this chapter, is because so many times when we start talking about economy, the first thing that we think about is material costs. But what can we do to reduce our material costs? And material costs are important. That's definitely a component of economizing the manufacturing of our precast. But material costs are not the only thing that need to be considered. We need to consider all these other processes as well. If material costs were the only thing that mattered, then nobody would be producing self-consolidating concrete because it has a higher cost per yard than a traditional slump concrete does. But if we take into consideration material costs and labor costs and energy costs, safety, all of those different things, then looking at that big picture, that's going to get us to the point where we're truly economizing the manufacturing of our precast and getting to a point where we're getting the manufacturing process to a point where we are most competitive and producing at the most economical level. All right, so it's just a very general discussion here at the end of the chapter. It's not any specifics, numbers, or anything like that. It's just primarily the reminder that when we're looking at economy, to keep the full process in mind. That includes materials, that includes batching and mixing, placing, consolidating, finishing, storage, transporting. It's the whole thing. So look at all of those aspects if you truly want to get your production and your provision of precast concrete to be the most cost-effective that it can. All right, so that is it for Chapter 2. Do we have any questions on Chapter 2? Any questions? All right, well, if there's no questions on Chapter 2, then we'll wrap things up for today. Just a little preview of tomorrow. We'll be looking at Chapter 3, which is properties of fresh concrete, and Chapter 4, properties of hardened concrete, and then we'll do the first half of Chapter 5, concrete mix design. Chance will be with you tomorrow going over these 2.5 chapters. We will have a break in the middle of the afternoon like we did today, and then we'll give a little preview tomorrow of what's coming up on Wednesday. But that's what tomorrow will look like. Lauren, do you have anything? All right, I'm getting a message from Lauren that that her audio is not functioning properly. So that'll wrap things up for today. If there are any questions from Chapter 2, then we'll certainly have time to field those first thing tomorrow. So Lauren, if there are any questions, just hang on to those, and when Chance starts up tomorrow, he can go ahead and address those questions.
Steve, can you hear me now? Oh,
Yeah, I can hear you.
Woo! There we go. I was like, why is this not working?
Yeah, I can hear you now. Great.
Fantastic. Okay, we did have a couple of questions.
Okay.
The first one was, how does the change from type 1 and type 1L affect the Bogue compounds?
It definitely, there's a bit of a shift in those. For those of you that have not encountered this yet, which I think most of you probably have, there's a move in the cement industry from a standard traditional type 1, or it's not just type 1, it's all the types, from a traditional cement to a limestone cement. And so basically what this is it's just your regular cement that they're adding ground limestone to. And the percentage may vary from one supplier to another. I know some suppliers are using like 8-9% limestone. And then I've heard of up to 13% limestone from some cement suppliers. So since it is raw limestone that's being added to the cement, that does shift the Bogue compounds somewhat. I would expect that the proportions of the Bogue compounds would be similar because limestone has a lot of the same oxides that your cement is going to have, since a good proportion of your cement is the natural product that it comes from is limestone anyway. So there is some shifting around of those Bogue compounds in the proportions, but overall, I would say there's not any significant changes that would cause any concern. One thing, probably the biggest concern, if there is a concern, is that the amount of C3S and C3A is probably less in the limestone cement. And so for most Portland cement applications, that's not a big deal. But for precasters, it is a big deal because it's the C3S and the C3A that give us our early strength. So there is talk of a type 3 limestone cement, which should help to alleviate those issues. But I know some precasters, especially precasters that have high initial strength requirements, like for certain types of bridge products, where you may need 5,000 or 6,000 psi just for stripping, that using limestone cement, it's really affected their production process because they just can't get the strength for stripping as quickly as what they used to when they weren't using the limestone cement. So as far as the Bogue compounds go, there is some shifting around, but as far as actual physical results of that, other than the more difficult to get early strength, I'm not aware of any significant issues.
All right. The next one we had is, how often should we be doing moistures in a day?
That will vary from plant to plant. If a plant has moisture probes on their aggregate stockpiles and the probes are functioning properly, then you should be doing moistures. I think the manual says regularly, just to confirm that the moisture probes are functioning properly. In the commentary in the manual, it says once per week. So if you have probes, then doing moisture tests once per week, just to make sure the probes are functioning properly, is fine. If you don't have probes, then at a minimum, you should be doing moistures at least once per day prior to the starting of batching. That would apply to plants that have indoor aggregate stockpiles. Some plants have indoor aggregate silos that they fill up each day. And so then the next morning, they filled it up the day before. So the next morning, they'll do some aggregate testing, some moisture testing to determine what kind of moisture level they should be using for that day. If the aggregate stockpiles are stored outside and it's a rainy day, and you're constantly taking aggregate from that outdoor stockpile and putting it in overhead bins, such that the moisture is kind of fluid, it's changing, then you need to be doing multiple moisture tests throughout the day, just to keep track of how that moisture is changing, so that you're properly adjusting the mix design.
All right, and the last question we had is, what happens if you go over any of those batching tolerances?
If you go over, just on occasion, it's usually not a big deal. If I'm doing an audit and I'm watching batching and I see a material batched out of tolerance, and it's just a random occurrence and it's just slightly out of tolerance, then usually I'm not too concerned about that. No process is perfect. That's just going to happen on occasion. But if I'm watching batching and it's a fairly common occurrence that a material is being batched out of tolerance, then that would be a nonconformance. The plant needs to be looking at why that material is regularly out of tolerance and making adjustments to their batching system to correct that. It's a much bigger deal if they're over on cement. Is not as big of a deal as if you're under on cement. If you're over on cement, you're wasting money, but at least you're not adversely affecting the properties of the concrete. But if you're regularly under batching cement, then that's a bigger deal because you're adversely affecting the performance of the concrete. So it depends on the material and it depends on how frequently the out of tolerance condition occurs.
All right, those are the only questions that have come in.
Okay.
So,
Well, if there are any other questions, then you guys can type those in at the start tomorrow, and I'm sure Chance will be able to answer questions before you actually get going with Chapter 3, if there's some that are available, some questions that are available.
all right. All right, thank you everybody for attending this session. Certificates of continuing education will appear on your account at www.rcep.net within 10 days. I generally enter these certificates on Mondays. I will try to do it throughout the week so you guys have an opportunity to see them. Remember that continuing education credit is given for each individual session. If you have any questions at all, please email me at lbell@pci.org. You will receive an email from our certification team. I spoke to them. They said they'll probably send it out on Wednesday with further information regarding the scheduling of your exam. This concludes this session. Thank you for attending and have a great evening, everybody.